Okay. Okay. So I select the pointer. Okay. Okay. Can you hear me? No? I cannot hear you, but I guess it's okay. So I start my presentation. So thank you very much for the kind invitation. And I would like also to thank all the organizers for organizing this meeting and for giving me the opportunity to present our work on oxide nanomechanics. And especially I would like to thank Mr. Dr. Bijwe for the invitation.
Hello, please. Hello, sir. Sir, sorry to disturb you. The next session will be starting 5 minutes.
It's still ongoing?
Yes, sir. Next session will be starting 5 minutes.
I have to wait?
Yes, sir. Yes.
Yeah, okay. Well, please let me know when,
Yes,
when it's
sir.
ready.
Yes, sir.
Hello, sir. Next session start will be 15 minutes, sir.
Yeah, okay.
Only 5 minutes wait.
बुके वालों को नहीं आएंगे. Venerable Sant Gadge Baba, renowned philanthropist, Venerable late Govindrao Dada Tompe, I at the very outset pay my respect to these greats and begin this technical session. Dear friends, today we are feeling very honored for having Honorable Dr. Gopal Dhokne sir as a chairman of this technical session. Dear friends, there are so many academic achievements of Dr. Gopal Dhokne sir in the arena of scholarship, but here I am putting forward only few of them. Dr. Gopal Dhokne sir, Associate Professor, Department of Physics, Arts, Science and Commerce College, Chikaldara, District Amravati. His educational qualification is MSc Physics in 1993 from Sant Gadge Baba Amravati University, Amravati. PhD in 2009 from Sant Gadge Baba Amravati University, Amravati. His teaching experience is 22 years, 7 months. Under his supervision, 2 students have been awarded PhD degree and 2 students registered for PhD degree. He is member Board of Studies in Physics at HGBAU Amravati. He is member Amravati University Physics Teachers Association. Ex-president HGBAU Shikshan Manch Amravati district. He has presented 32 research papers at international and national conferences. He delivered 6 guest lectures at various colleges. Before commencing to the proceeding of this technical session, it is my duty to welcome to the guest of the session. For having Dr. Gopal Dhokne sir as the chairperson of this session, I request Dr. Rajendra Ramteke sir to welcome him by offering the memento, sapling and floor. I request Dr. Ramteke sir to welcome him by offering the memento, sampling, and follow. Today's speaker, Jejev Salisa, Head Department of Physics, KBC, North Maharashtra University, Jalgaon. He is joining with us in online mode. I welcome you, sir, with a kind words. Our next speaker, Dr. Luca Pellegrino, CNR SPIN, Genoa, Italy. He is also joining with us. In online mode. I also welcome you, sir. Our another speaker, Dr. Nilesh Tarwal, sir, from Shivaji University, Kolhapur. I request Dr. Parimal, sir, to welcome him by offering memento, sapling, and full oath. Dr. Nilesh Tarwal, sir. Dear friends, without killing much time, I request to Dr. Dhokne, sir, please introduce our speaker, and I am handing the session to Dr. Gopal Dhokne, sir. Thank you. Okay. Hello. Good morning to one and all. First of all, I would like to welcome honorable resource person, honorable speakers, faculty members from the various university, various colleges, researchers, teaching and non-teaching staff of this college. On the behalf of organizing committee and as a chairman of this fourth technical session, again I welcome all of you. In this fourth technical session of second international conference, that is Raman 2022, there will be two plenary talks and one invited talk. The first plenary talk will be delivered by Professor Dr. Jejev Salisa. Second plenary talk will be delivered by Dr. Luca Pellegrino, and the invited talk will be delivered by Nilesh Tarwal, sir. Again, I welcome all of you. Now, I would like to take an opportunity to introduce Dr. Luca Pellegrino, sir. Dr. Luca, sir, welcomes you and good afternoon to you. सरांचा आवाज येतो आहे का?
Yeah.
Dr.
Can
Luca,
you hear
sir.
me? Can you hear me? Hello? Can you hear me? Can you hear me?
Yes. Okay.
Okay.
Sir, welcome.
Thank you.
Dr. Luca, sir, presently working as a permanent research scientist at CNR Steam Unit of Genoa, Italy. He received his PhD degree in 2004 from the University of Genoa. Professor Professor Luca, sir, has awarded 2 times for his outstanding work on nanometric patterning techniques of oxides and realization of innovative nano devices that allow the investigation of conduction mechanics in complex oxide at nanometer scale. Again, he got second award for the participation to national and international projects. Dr. Luca uh, conveyed various national and international projects. He worked as a coordinator for the Horizon 2020 Fed Open project. Then he worked as a coordinator for bilateral project 2018-19 between the National Research Council, CNR, and the Japan Society for the Promotion of Science. Again, he worked as a coordinator for joint research project and particular relevance. The project title was solid state actuators of micro nanoparticles. Then Dr. Luca working as a member on the various committees or councils. He working as a member of scientific technical committee of START, member of the outreach and dimensions working group of CNR Spain. Then he organized the two conferences and workshops also, and he got two patents. Out of two, one is the European patent, which was on micromechanical thin film devices of transition metal oxide and manufacturing methods, and his second patent on, that is IT patent, and that was on selective simulation of small nerve fibers of micropattern integrated surface electrodes. Dr. Luca has a very huge biodata, but due to time constraint, again I invite to deliver his plenary talk on the topic. Dr. Luca sir, please, you may continue your lecture. Dr. Luca sir, please.
Thank you. Thank you, Mr. Chairman, for your kind introduction. And thank you to all the organizers of this meeting for inviting me to present our work. Today, I would like to discuss our activities in oxide nanomechanics. These activities have been pushed during the years, and I will show you now some examples of what we did in collaboration with other groups. And I guess you might see my screen now. Okay, I hope you can see the full screen. Okay, I will start. Can you see the full screen?
Yes, sir. You may start now.
Okay. Okay, thank you. Okay, so this is the outline of my talk, and I will briefly make an introduction to oxide microelectromechanical system. Then I will discuss about the fabrication processes to produce these oxide MEMS. Then I will move to 5 applications of our devices. I will just briefly outline these applications. So I'm from the National Research Council of Italy. In particular, I'm from the SPIN Institute, whose topics are innovative materials and application for electronics and energy. SPIN is the acronym of superconductors, oxides, and other innovative materials and devices. We have 5 venues, 5 laboratories across Italy, and I come from the SPIN Genova. You can find details of our institute in the website. Micro electromechanical system and nano electromechanical system are usually made with silicon materials or silicon-based materials, like silicon nitride, for example, or silicon for the industry. There are well-developed processes, well-known mechanical properties, and I mean, there are state-of-the-art nanomechanical devices, but people would like to increase the functionalities of these devices by adding new materials. And in particular, oxides are very interesting material because they exhibit a lot of physical properties. For example, they can be transparent conductors, they can be insulators, they can be superconductors, they can be magnetic, they have also thermoelectric properties, they have multiferroic behavior, and they are also very sensitive to strain. So what we are doing is to develop nanomechanical and microelectromechanical system by have a direct route to fabricate oxides on oxides. So we completely avoid the use of silicon, but we try to make MEMS using silicon, using oxides, and in particular we do pulse laser deposition of thin oxide films and aerostructures. And what we do is to make a new type of structures starting from multi-layers or thin films. So this field is quite to be developed. So we are going to fabricate and to develop new processes to study the mechanical properties of these devices and make experiments. I will show you some examples. So this is what we are doing. So the basic structures for this oxide MEMS is the freestanding element, and we have two different routes to fabricate this freestanding element. One is to make a deposition, a sacrificial layer, and then to do patterning by photolithography, and to release the freestanding element by selective acids. I will show you an example, and we do this by pulse laser deposition. And this is an example of a strontium titanate cantilever. Strontium titanate is a well-known oxide that we employ for growing a lot of oxide materials. Is an insulating oxide. So if we do a sacrificial layer made with these manganese oxides, we can fabricate the pattern, and then we can release this using chlorhydric acid, because chlorhydric acid does not affect strontium titanate. So we remove below the film. Secondly, we can use a substrate. We can also remove the substrate, and this is a second example. Here we grow a manganite film, which is this one, on STO. In such a case, we can use fluorhydric acid, which affects STO, but does not etch manganite, LSMO. So we do patterning by photolithography, and then you can see in this image here that progressively the acid is removing the part of the substrate, and the light area here, the yellow part, means that the substrate underneath the microbridge is totally removed. And you can see here from this same image what we can do. This is a freestanding manganite bridge, which is 100 nanometer thick, and the width is about 2-3 microns, 5 microns. And I will show you an example later on. We have the same process using vanadium dioxide. This is done in collaboration with Japan. I'll show you later. And this is a freestanding cantilever that is made on MgO 100 substrate, and we use phosphoric acid to remove the MgO that does not etch vanadium dioxide. So we etch all these films instead of using argon milling that we can use to remove the structure easily. So this is the main receipt that we use to fabricate the structures, and then I will move to show another example more, and that even choosing the right crystallographic orientation of the same substrate, which is STO, we can have different fabrication conditions. For example, we can have rough surfaces after etching or smooth surfaces after etching, and we can tune the geometry of the clamped regions with different by choosing the proper orientation. I will not go into detail of this recent paper, that please you can refer here to further information. Okay, so why using freestanding oxide? So we have three types of experiments in mind. One is the strain bending. So if you have for example, a crystalline structure, we can bend it and we can apply strain. We can have localized heating by flowing current into the freestanding structure. The freestanding structure does not change heat with the environment easily as clamped films, because you do not have the heat conduction through the substrate. So you can heat up a lot with a small amount of energy. And then we are studying also what happens if we are moving the structure and we are detecting the resonance frequencies of our microstructures. So first example is strain devices through bending. So here is an example of a strontium titanate cantilever, as I showed you before. On top of this, we can deposit film by pulse laser deposition. So we can place this structure in our pulse laser deposition chamber and deposit all over on top the film, which grows epitaxially. And we have a good quality of the films. And this is an example of cobalt oxide films made by Michele Biasotti a long time ago, but shows that we can tune the strain. This is the strain, this is the resistance due to the increased strain in this structure as a function of the gate. So with the gate, we can bend the structure. At the end, we study the conduction of this structure here. And in this place, this is a cross section, but you can see here, in this place, we change the strain. We have tensile strain, and by strain, we change the distance between the ions of the cobalt oxide. So we modulate, and you can see here that we can modulate the structure at different temperature. So these devices are a way to study the conduction properties of oxides, epitaxial oxides, and as a function of the strain, and we can achieve a maximum strain of 0.26%, which is quite a lot in this structure, which is about 300 nanometer thick. So now I move with a wonderful material, which is vanadium dioxide, and we are studying this material since a lot of time in collaboration with Japan, and they are doing the nice films with a very nice quality. And we are also performing experiments by fabricating MEMS and making the measurements. So I just briefly outlined some of the main properties of this material. So this oxide has a transition, a resistive transition, a phase transition at above room temperature at about 70 degrees Celsius, and which is quite sharp. This is made from a film and is 4 orders of magnitude. And at the same time, you have a change of the crystalline structure from monoclinic to rutile. So this change of crystalline structures has a lot of energy inside. So it's a reversible strain, which is about 1% along the C-axis, and negative, so you have a contraction, and a positive in the AB axis of the cell. In the small temperature windows, you have a lot of strain energy density. So if you see this graph from this reference, you see this is a logarithmic scale. You have a lot of energy, which is more than piezoelectric materials, electrostatics, and is comparable, less, but to shell memory alloy, which are, the most energy actuators that can be used, or solid liquid transition. So this material has a lot of energy during this transition. I will show you some later on, some example of what we did, but also I would like to focus that this transition from low temperature insulating to high temperature metallic state as an hysteresis, and in this temperature windows, you have a mixed state between these two phases. So you have a mixed state that I will show you how we can detect it. So this is MEMS. The black part here is freestanding, And this is the cantilever that in the meantime we can study the conduction. And this is made by using a vanadium dioxide film with a thickness with titanium oxide buffer layer to allow the best grow conditions on MgO substrate. Then, as said before, we fabricated the device, and then this is a picture from optical microscope of the device. And what we did was to measure the resistance as a function of temperature. Here you can see the transition, the resistive transition. This is logarithmic scale. And at the same time, here you can see the change of the frequency, the oscillation frequency, because we also make this cantilever oscillating by a laser, and by electrostatic actuation we can detect this microstructure. So at the same time, meantime, we measure the resistance, we measure the resonance frequency, the Huygens frequency. And we see that we have this transition. At the same time, we have a change of resonance frequency. And this is due to the fact that by changing the temperature, this film changes both the electrical resistance and the internal stress due to the change of the lattice structures. So at the same time, we have internal stress, and as you know, the stress can change the resonance frequency of freestanding. You might know that. If we have a microbridge, for example, we do stress it, we can change the resonance frequency of a wire or of another structure. So we can do even more. We can stay in this temperature window by thermalizing the sample, and we can apply a current, a strong current, not a strong, but quite relevant current, so to heat up the system. And if we heat up the system here, and we have heating in this, the heating is concentrated in this region, we can change also the conductivity, because in this region, we have a mixed state between metallic rutile structures and insulating monoclinic structures. And you can see that later on, we can play with the current to change the ratio between these structures. So meantime, we play with the current, we measure the electrical resistance, and we see that we can tune the electrical resistance here after current pulses, because we program the ratio between the metallic and insulating state. This works only in this temperature window, because if we cool down the system, we completely erase these regions. And so we have both effects, both resistive and a mechanical effect. And by changing the amount of current pulses, we can program the eigenfrequency. So we have a mechanical memory, or we can program in a multi-state the electrical resistance. So we have a programmed resistive memory. So we're not going to details, and you can find details in these two papers on how we can reach this multi-state. Anyway, we are working in the hysteresis windows of this phase transition. And so we play with the stress, and we play with the electrical resistance of the material. Another interesting effect, this is somehow the core of using epitaxial oxide, that is mainly due to the fact that we are growing oxides on oxide substrate, so we can completely exploit epitaxial grow properties. We can grow vanadium dioxide and titanium oxide layers on MgO 001 or MgO 110. And if we go this in 001 substrate, we have isotropic behavior, because the domains, the films grow with a z-axis on the plane, but we have two orthogonal domains. Instead, if we grow on MgO 110, the z-axis on the plane, but the films are oriented as a single crystal. So we have some anisotropic behavior that is clearly demonstrated by the next slide, where we fabricated the microbridges onto different substrates, MgO, and this is on MgO 001 at low temperature. This is an optical profilometer image. This is a freestanding vanadium dioxide. At low temperature, the films is in the two direction are bent due to the fact that the films are slightly compressed. So when you release from the substrate, they bend. But if you heat up above the transition temperature, you have this transition, of course, because you are changing. You have a contraction. You are changing the lattice parameters. Instead, if you are working with MgO 110 films, you have a very interesting behavior due to the anisotropy. We have the c-axis direction, and you heat up. You have the phase transition. You have a contraction, full contraction, and you have the bridge that is really changing the bending. But on the other side, you have expansion. So you have the bridge that is changing from flat to bended conditions. So this is very interesting, as on the same sample, you can have, by heating, you can have these two behavior. And we show you a movie. So where here, you can try to, I have to, okay. As you can see here, we are heating the sample in one direction. You see here that is changing the shape. Even the freestanding region are here. So you see, and the bend is changing. And here, the opposite behavior. You are heating up the system. This will stress, will strain, and this will compress. And even the bridge will compress. You see, again, I will show you again. The bridge is tensile strain, and then you have compression, so the bridge is bending. This video is made during the heating of the system across the phase transition. I move now to another application of the actuators, exploiting the energy of this film, this material. So we grow the films, we do the patterning by ion etching, and then we grow on top again another film. This is to have a large aspect ratio of our structures, and what we fabricated is what is so-called a chevron type vanadium dioxide actuators. So this is all freestanding. And then when you heat up the systems across the transition, the films will change the lattice parameter. And I will show you now. You can find this in these publications. The system is moving. These are actuators made below the transition temperature and above the transition temperature. This dimension here is about 20 micron. So they are very tiny structure, which are thick about 300 nanometers. So it's quite thick compared to what is called a thin films in some sense. And you can see this is moving of several hundreds of nanometers by heating up the sample, but we can heat the sample even with a laser. This is a blue laser heating the sample. So you go with the laser, you heat up the sample, heat is diffusing the heat across the sample leg here. You are increasing, and then you are moving the sample. And just want to say that if you want to move the sample, if this sample was a normal, this would not move like this, because the change of in these small temperature windows, the change of the strain on our sample is quite large, which is tens of %, which is quite large for systems. If you use gold, for example, is a gold structure would change very few, because the thermal expansion in 5-10 degrees is very small value. Now I will show you another example of mechanical actuators, which is quite interesting. This was done in collaboration also with the Technical University of Delft, and of course the Institute for Scientific Research in Japan. And this is a freestanding bridge made with vanadium dioxide with two metallic pads here, and here is the cross section. Here you have vanadium dioxide structure, and if you apply a DC voltage, you have a here a resistance, a variable resistance. I will not go into detail, but what happens is that these systems goes to metallic and then go back to the insulating state, and you have this kind of oscillating behavior due to the instability of this and the energy that comes from the DC voltage. So this becomes metallic. Once it becomes metallic, you get less energy due to Joule effect. Then it go cool down again and becomes insulating. And then it gets again in the insulating state, but then it ups due to the current by Joule effect, and they go back to the metallic states. And again, in the metallic states, the Joule effect is lower because the resistance is lower. For the same current, you have less energy, so that you go back to the insulating state. So you have some kind of electrical oscillation that depends on the amount of voltage and on the amount of the resistance you place in series with this device. And at the end, if you do measure the mechanical properties of this device, so by a laser, for example, with a small power, so that you do not influence the thermal properties of this device, here is the gold pad. So you are hitting only this small region of fill by Joule effect. You see that for some particular periods, your device is moving. This because you are matching the oscillation of this voltage with the mechanical resonance of this microbridge. And so by changing this resistance, you have periodic phase transition, and then you have mechanical excitation. So this VO2 region work as a micro engine, which is powered by a DC bias. So this could be particularly interesting if you want to do integrated actuators without electronics. I mean, we can use only DC bias, which is quite easy to make. Of course, this vanadium dioxide transition takes quite a lot of energy, because the energy associated with this phase transition is quite high, but at the same time you have quite large force and power. We now change material, and then we now move to manganese oxides. Manganites, they are quite famous oxides in the oxide panorama, because they have magnetic transitions, and this is a particular the phase diagram of manganite with lanthanum and strontium. And depending on the lanthanum strontium stoichiometry, you have different behavior. Here you have paramagnetic and ferromagnetic metallic behavior, and in particular the 0703 composition have this phase transition above room temperature. And the phase transition can be detected and measure the magnetic behavior. At the same time, you can also see the change of resistance is quite large. You have this metallic behavior, and this kink is related to this magnetic transition. And this is particularly interesting, as it has been proposed to make bolometers generally, because of the relative change of resistance with temperature is quite large compared to other materials, and you have also low noise in the resistive characterization of these materials. But I will show you other application now on these materials, and of course we are making microbridges with manganite. This is quite short microbridge, and I would like to show that you can heat up the microbridge in air conditions, and you have light here due to the high temperature that you have in this place, and you flow about 600 micron ampere. You have about 1 milliwatt of electrical power inside the structure, and you have red light, which is due to the fact that you are heating up the sample. You do not oxidize because you already have an oxide, so you can work at room temperature. So this can work as a micro hot plate. And I will now show you how we can use these heating properties of these microbridges to make some kind of memory, which is quite interesting to me, because you can heat up the sample, as I said before, both in air condition and also in vacuum conditions. So I said before, this diagram taken from this reference show that the material has a plating behavior. If you have small strontium inside, small amount of strontium, and you have metallic behavior if the stoichiometry is, for example, 0.25 or 0.3, and you have this magnetic phase transition, which decrease the temperature by changing the content of strontium. But you can even keep the strontium content constant and change the oxygen stoichiometry, and this can be done dynamically and in real time by changing the temperature of the system in vacuum conditions. So you place, this is the resistive behavior of lanthanum strontium in this stoichiometry, and then you can apply a pulse. As I showed you before, you heat up the sample to high temperature. We could not measure the temperature, but I guess it's above 600 degrees. You see the light coming from the sample. And you take out oxygen because you are in vacuum. And so you completely change not only the resistance, but even the magnetic behavior, because here you have a ferromagnetic metal, and then here you have an insulating non-magnetic compound. You have no magnetism in this place because the resistive behavior is associated to the magnetic behavior of the sample. Of course, you are tuning the properties only in this region where you increase the temperature. So you can back by heating the sample in oxygen atmosphere, and you go back here, and you almost recover the original ferromagnetic state. So this is kind of an example of how you can use particular materials that you can tune reversibly, and not only the resistance, but even the magnetic property, structural properties by changing the conditions. I show you before, you can change the ratio of the domains in vanadium dioxide. This is just only the phase transition, but in this case, you can even change the stoichiometry of oxygen. So this is another example of the advantages of making freestanding extraction with these oxide epitaxial films. Now move to another topic we are doing right now. This is a freestanding manganite bridge, which is very long, as you can see here, 200 microns. The yellow part is freestanding, is very nice structure, and this double clamp and micro bridge was done on 110 STO, and this is the mechanical resonance, and this is the mechanical spectrum. You see the first mode, second mode, and the other mode here, and this is the resonance of this structure, which is quite large Q factor. And even in this case, we can detect the change of resistance associated to the magnetic phase transition of this structure as a function of temperature. At the same time, we can observe a change of resonance frequency. This is due to the change of the Young modulus, because here you have a magnetic transition. So you change the Young modulus and you change the tensile stress of this structure here. So tensile stress is linked to the change of the resonance frequency of these mechanical structures. And in this region where you have the resistance, you have also change behavior of the frequency due to the change of tensile stress. At low temperature, we argue that this is due to the change of the Young modulus by this kink, and above this temperature is probably a combination of the change of Young modulus and the change of thermal expansion coefficient of the films with respect to the substrate. So details will be soon, will appear soon, as we recently submitted this article. So it's time to conclude. These are the conclusions. I show you this complex oxides offer good opportunities for developing microelectromechanical sensors and actuators with enriched functionalities. I show you two examples of two interesting materials. One is vanadium dioxide, it's showing some memory effect and some actuators, and also a magnetic manganite, showing that we can use this compounds, even for making some experiment with the micro hot plate by changing the oxygen stoichiometry and study the effect of the change of the oxygen stoichiometry on the physical properties. And also I show you some preview on using this manganite freestanding structure as mechanical resonators. And I would like, before concluding, to give knowledge to the wonderful work of people that collaborate on these topics. And first of all, I would like to thank all the PhD students that developed these structures, in particular Michele Biasotti, Nicola Manca, Federico Remaggi, master students Valentina Cerniale, and staff members of CNR, Cristina Bernini, Emilio Bellingeri, Professor Siri, and Professor Daniele Mare from University of Genova. And I would like to also acknowledge the development of VO2 MEMS that has been done in collaboration with Professor Kanki and Professor Tanaka during those years. We have a long time collaboration with this Institute of Industrial and Scientific and Industrial Research from Osaka University. And in particular, we got this bilateral project that now is at the end. And you can see our results in this website, which is still active. And this was done a good collaboration between our and the Japanese group by exchanging also students and visits. And of course, I show also you a collaboration with the Technical University of Delft. Nicola had a postdoc in this university a few years ago, and so he developed also the resonant micro actuators. And at the end, I would like to mention that we are working now in a project, a European project, which is dealing with oxide nanomechanics and on the development of sensors with oxides, in particular magnetometers. And I would like to acknowledge the work of the people in the unit of Genova, in particular Nicola, that made a lot of works on this manganite and vanadium dioxide microstructure, Alejandro Plaza, that developed films and of manganite and other compounds of oxides. And now we have students and of all the staff members from CNR and University of Genova working this. And of course, the collaborator of the Oxygen project. Please check the website of this project. It's still active, and we will soon post news on our results. And so before concluding, I would like to thank you for the attention, and I'm very happy to have this connection with you and see your activities. So thank you very much again. So if you have any question, please. Okay.
Hello, sir. Am I audible? Hello, Dr. Luca, sir.
Yes.
Am I audible?
Can you hear me?
Hello. Am I audible?
Yeah.
Okay. Sir, thanks for
please.
Your today's lecture. I think it's very beneficial and informative and also useful for all of us. The new researcher will be definitely motivated for the lecture. Now the topic is open for discussion. If you have any query regarding oxide nanomechanics, you may ask. Yes, anyone? Hello, sir.
Yes.
One question to you. Regarding oxide nanomechanics.
Can you speak near the microphone? Because I cannot hear you so much.
Okay. Without mic, I can talk. Mic showing good. Hello. Now am I audible, sir?
Yeah.
Okay. How the physical properties of complex oxide will be changed, or which technique will be used for changing the physical properties of the oxide?
So you're asking me which technique I'm using to change the physical properties of oxides. Is it right? Okay.
Yes, sir.
Okay. So basically, when you deposit oxides on substrates, okay, they have their properties, their bark properties can be measured with different techniques. This depends on the oxides. For example, you can measure the magnetic properties of the optical properties.
Only physical properties, sir.
Only the
physical properties.
Yes. Physical. So you mean the electrical properties?
Hello.
So the physical properties can change with the temperature, for example.
Yes.
Yeah. So what we are doing is to change the physical properties usually by temperature, both by changing the temperature of the sample in a sample holder, or by changing the temperature by Joule effect, by the current. So these oxides, usually the phase transition depends on the temperature. Also, the phase transition depends also on the strain.
बघता का बस
Yes.
1 मिनिट फक्त हाँ ओके सर ओके सर थँक्स अगेन on the behalf of organizing committee again Dr. J.R. Dhokne, thanks for your nice and informative presentation. Thank you so much, sir.
Thank you.
Now in this fourth technical session, the second plenary talk, I would like to invite Dr. Jejev Salisa. Yes, Dr. Jejev Salisa, am I audible?
Yes. Good afternoon, sir.
Hello.
Yes, you are audible.
Salisa.
Yes, I am getting your.
Jejev Salisa, am I audible to you?
Yes. Yes, you are audible. Hello.
Hello. Yes, sir. Am I audible to you?
Hello. Hello.
Hello. In this fourth technical session, the second plenary talk will be delivered by Professor Dr. Jejev Salisa. Now I would like to take an opportunity to introduce Dr. Salisa. Dr. Jejev Salisa presently working as a professor and head in the Department of Physics, North Maharashtra University, Jalgaon. Dr. Jejev Salisa have again huge CV. He has completed 9 research projects funded by various funding agencies like UGC, DAE, DST, Women Scientist Scheme, then ACRB. He has completed 9 projects, major and minor 9 projects. Under the able guidance of Dr. Jejev Salisa, 2 students submitted their proposal and also approved for the Inspire Fellowship. 9 students have been awarded by PhD degree under the guidance of Dr. Salisa. He has present number of research papers in the international reputed journals. He is working as a member of Committee of Science Textbook. He created and administrating the group that is Physics Katta. He work and working as a coordinator for Physics Katta. Now again I request to Dr. Jejev Salisa to deliver his lecture. Please, Jejev Salisa, you may continue now.
Thank you very much. Am I audible?
Okay,
Hello. Am I audible? Hello.
Hello.
Good afternoon, sir. Am I audible?
Yes. Clearly, you are clearly audible.
Okay, thank you very much. So,
Okay, sir. Welcome.
Good afternoon.
Welcome, sir.
Yeah, good afternoon to all of you. At the
Thank you.
onset, I thank the chairman of the conference, Principal R.S. Ramteke, then convener Dr. D.R. Bijbe, as well as my friend Dr. Hoover
Don't do what I
for inviting me to this conference, Raman 2022. So I will just share my presentation with you. All right. All right. So I hope the presentation is visible. Is it? Kindly let me know if the presentation is visible. Okay. So this is the title of my talk today. Myself, Professor Jejev Salisa from the Department of Physics, and this is my university picture. Today, I will be talking on the one topic that we are dealing with, that is related with the perovskite solar cell. The title is perovskite fullerene bulk heterojunction using a microemulsion scheme. I will talk about the modeling, simulation, and experimental studies that we have done at the Department of Physics. As I have come to know that the audience okay. The audience is mixed. I mean, the audience also contains the students at master's level, then research students, as well as the researchers, professors from different college and institutes. So I will spare few minutes or some part of my presentation on some basic topics, and then eventually I will lead to the problem on which my group is working. So as you can see, presently the commercial market related to the photovoltaics is mostly dominated by crystalline silicon solar cells. We can say about 98% of the photovoltaic modules available in the market, they are either made of monocrystalline silicon solar cell or polycrystalline silicon solar cell. These are called as first generation solar cells. And the price of this photovoltaic solar energy has dropped significantly over the past few years. And presently today, it is well below about $0.50 per watt. So when I was working as a research student on amorphous silicon solar cell, at that time, people used to say that this is the dream of photovoltaic community, to bring down the price of silicon solar cell down to $1. Now it is $0.50 per watt. But even the research in photovoltaics is still continued because the demand for clean energy is ever increasing, and of course the objective of mankind is to have the clean energy in maximum possible way. So there are chances, of course, to decrease the cost of solar energy further. As we know that silicon solar cell thickness is about 300 micron, and most of the cost of silicon photovoltaic technology goes to the material cost as well as the energy involved in getting pure silicon. So efforts in photovoltaic research community are towards developing new materials for thin film solar cells, and that used to be called second generation solar cell technology. So many thin films were tried, many materials were tried, and now we are in the third generation solar cell technology, where quantum dot solar cells, then dye sensitized solar cells are being tested. And recently, I mean, not so recently, for the last 10 years, a new candidate has come up, which is the perovskite solar cell. So in this presentation, I will talk something about the perovskite solar cell and the work we are doing in this area. So the thin film solar cells, in which of course we can include the perovskite solar cell, the thickness of the solar cell is very, very less. I mean, it is about 300 to 500 nanometer. Just now I told that crystalline silicon solar cell thickness is about 300 micrometer. So thickness of thin film solar cell is about 1,000 times less than silicon solar cells. So if we can successfully commercialize such solar cells, then cost will be drastically drop. It will be drastically reduced. Secondly, the technology that is needed for thin film solar cells is very, very easy. We can have solution processable methods for printing the thin film solar cells. So both these factors can lead to very cheap solar energy in future if we can successfully overcome the obstacles which are presently there in case of the thin film solar cells. So when we talk about any solar cell technology, naturally we have to see that what is the progress of this technology right from its beginning. So as far as the perovskite solar cells are concerned, the true work on this solar cell started back in 2012, about 10 years back, and the progress made in this field is surprising. I mean, over the past 10 years, the efficiency has reached to the level of crystalline silicon solar cells. So there is no such example in photovoltaics, which shows that during such a short period, it has attained a very high efficiency. So in this way, we can say that perovskite solar cell is a promising option. If we can overcome the hurdles which are presently there, it can be a promising option which can replace the crystalline solar cell by a cheap option. There is another advantage of using a perovskite as compared to the other candidates for thin films. So this is a chart wherein you can see that it shows the ratio of open circuit voltage and the band gap for different materials. On x-axis, you can see there are different materials are there, and y-axis shows the ratio of open circuit voltage and the band gap. So here there is a relation which relates the open circuit voltage with the band gap. Okay, so ideally the ratio should be 1, but as you can see, there are different losses present, recombination losses present in the optical devices, and that makes this ratio much less than 1. So having this VOC by EG ratio expressed in percent as much high as possible is a indication of a good candidate for solar cell technology. So here lies the perovskite material. You can see it is having VOC by EG ratio more than 70%, indicating much less losses, optical losses in this material. So as I have told that in the last 12 years, we have got a very good performance as far as perovskite solar cell is concerned, and every year we get a news that this and that group has achieved a world record efficiency. So this was a news last year. Ulsan National Institute of Science and Technology from South Korea, the scientists could achieve very high efficiency, 25.8% efficiency for perovskite solar cells. And this work has been published in Nature. Okay, so this diagram shows a generalized structure of a perovskite solar cell and the new things, the new way they have employed in the fabrication of perovskite solar cell, which led them to have a very high efficiency. All right. Okay. So thus we have seen that the perovskite solar cells, they have become a rising star of photovoltaic world, and they have created a very huge interest to the scientific community. Now, as I have earlier mentioned that there are some students in the audience who are doing masters or doing research in different areas. So for them, few basic things about what is perovskite. Basically, perovskite is a name of a mineral that was first found in Russia, and this specific, I think this is made up of calcium, titanium, and oxide. So after the founder of the Russian Geographical Society, Leo Perovsky, this material was named as a perovskite. So the materials which are having the same structure as the perovskite mineral, they are termed as perovskite structures or the perovskite materials. So this is a typical perovskite structure wherein it is frequently denoted by or expressed by this terminology ABX3. Okay, so where this A is an organic cation, mostly the perovskite photovoltaic material that is being used by research community, there this A position is occupied by methyl ammonium cation, that is CH3NH3, or a formaminidium that is NH2CH NH2 cation. Okay, so this position is occupied by same methyl ammonium cation. Then at the corners of this cubical structure, we have inorganic cation, that is B. Okay, usually it is lead. And at the center of these 6 faces, we have slightly smaller halogen ions. So normally these halogen ions include fluorine or iodine or bromine. So this is a typical ABX3 structure called as perovskite structure. Now this left-hand side structure is drawn with the inorganic cation at 000 position. On the right-hand side, the same structure has been drawn with the organic cation, that is CH3NH3, at the 000 position. So basically, both these structures are same. The way they are drawn is different. Now, as I have mentioned, the perovskite structures are specified as ABX3, and these are called as organo. A is an organic ion we have seen, so organo. B is an inorganic metal ion, so organometal, and X is normally a halide. And since there are 3 such atoms, we call as organometal trihalide. Okay, so as I have told, with the majority of the efficient perovskite materials that are being used in photovoltaic community, they contain specifically lead as the metallic element, and lead-based perovskite solar cells are particularly good because they show various range of factors which are really useful to be used as a photovoltaic material. As we know, this is on the right-hand side. There is a typical structural diagram for a perovskite solar cell. planar diagram for a perovskite solar cell, which contains different layers that are used in such solar cell structure. So a perovskite material is a photoactive material which absorbs the light and generates the free electron hole pair. So naturally, it must have a strong absorption in the visible regime. So a lead-based perovskite solar cells, they show a strong absorption in visible range. Secondly, once the free charges are created in the perovskite, they must be diffused towards the respective electrodes. That I mean, towards the hole transport layer, towards the electron transport layer. So they must have a long diffusion length, so that they will reach to the hole transport layer or electron transport layer without recombination. Therefore, a perovskite material having a long charge carrier diffusion length is desired, and lead-based perovskite materials should have this property. Thirdly, by changing its configuration by doping, you can tune the band gap, so we can have a tunable band gap. And last and most important is it has the ability to synthesize the thin films for solar cells at low temperature with a solution processable technology. So it has a easy manufacturing capability. Okay. But remember that perovskite materials are not solely useful, not only in photovoltaics, but they find application in many other fields as well. For example, superconductivity, then giant magnetoresistance, and spintronics also. Thus, the perovskites offer an exciting playground for the physicists, chemists, and material scientists. Okay. Now, how it compare with the present leader in the market? Present leader in the market is silicon solar cell. Okay. So as far as cost is concerned, the silicon solar cells are comparatively expensive because they are expensive to purify. But of course, as I have told you, that mass production has resulted in significant cost reduction. But perovskite solar cells have the advantage that, as I have told, they are mainly solution processable, and so they will lower the manufacturing cost tremendously. Now, what about the efficiency? We have seen that single crystal solar cells, they have efficiency in the range of 25-26%. And right now we have also seen that the perovskite are also at limit. So as far as efficiency and cost are concerned, silicon and perovskite both are comparable. What about the durability? Here we know that silicon solar cells last up to about 25 years. This is the minimum operational life for the silicon solar cells. However, presently, the longest reported perovskite stability is only 1 year. Now here, this is the major hurdle in the commercialization of perovskites as a material for photovoltaic technology. Durability. Now, to have perovskite as a good option for a solar cell, it must show satisfy certain criteria. It must have a power conversion efficiency of 10% for at least 10 years. These are some, say, thumb rules for a successful photovoltaic candidate. To compete the crystalline solar cell, it needs life of 24 years in outdoor conditions. Okay, and according to the International Electrochemical Commission's standards, solar cell must perform under non-laboratory conditions such as damp condition, 85% humidity at 85 degrees Celsius, and they must withstand such harsh condition for more than 1,000 hours consistently. Okay, but here the perovskite material fails. So in order to enter the current market, the durability of the perovskite solar cells must be improved, and most of the present research efforts are focused towards the stability of the perovskite material. Okay. Now, where are the problems as far as the stability is concerned? So, long-term instability of the perovskite is because of external factors as well as intrinsic factors. Okay. So, what are the external factors? when perovskite material is exposed to moisture, say water, oxygen, it leads to instability. And because of temperature, intrinsically, its structure can degrade. So we have to overcome these effects in the perovskite. Now, this is a typical crystalline structure of a perovskite. Okay, moisture that is present in the ambient, and so ambient humidity can cause degradation of the perovskite films. Specifically, this is MAPBI, I mean methyl ammonium lead trihalide. Okay? This is a typical perovskite that is being used widely in solar cell fabrication at a research level. The rate of deterioration because of the moisture also increases with temperature. Now, there are various reasons behind this deterioration. The one of the causes that the organic cation that we have seen, A, okay, that is used in perovskite solar cell, they are hygroscopic. So what happens? Water molecules, when they penetrate the perovskite film, they form weak hydrogen bonds with the cations, and this leads to the formation of hydrated perovskite phase. Of course, this change is reversible. However, when enough moisture is penetrated, then the perovskite crystal decomposes. So here are certain chemical reactions which have been identified, which can be the cause of degradation of the perovskite phase. So as you can see here, initially we have CH3, NH3, PbI3, MAPBI3 as a perovskite structure. When it has a reaction with H2O, through successive reactions, ultimately you can see that it can create separate the iodine from the composite, and then it can also create water molecules. Okay, so it can be looked at as a cyclic process, means because in the presence of H2O, it not only degrades the original material, but it creates additional water molecules also, which further cause further degradation. Okay, so if such thing happens, then the performance of the photoactive layer is definitely degraded. So what we can do for this? What are the possible options for this? Firstly, increase the strength of the bond between the organic component and metal halide. Okay, so you can choose different options for the A and B positions. It is extremely important that active layers be deposited in environment where humidity is controlled. So there are many studies how the humidity is affecting, humidity during manufacturing is affecting the perovskite. So we have to have a controlled humidity environment for manufacturing of the thin films, and the hydrophobic interlayers can be introduced in between certain layers. We can introduce hydrophobic interlayers which will protect the perovskite from ambient moisture. Okay, now the second possible cause of degradation of the perovskite is oxygen-rich environment. Okay, and there are some intrinsic factors, as I have told you, that if the temperature is goes high, then it can also lead to degradation of the perovskite. So during perovskite film formation, there are vacancies in the perovskite structure. As you can see here, there is one vacancy, here there is one vacancy. So at high temperature, it can lead to diffusive movement of different ions in the perovskite, and it can cause the deformation or the degradation of the perovskite phase. Okay, now all right, I will directly go to another the solution for this, what we can do for this, or what we are doing. Okay, as you can see, there are different options. People are trying different ways to overcome the perovskite instability. They are using mixed halide structures like bromine and chlorine along with the iodine. Okay, so if you just use mixed halides like iodine, bromine, and chlorine, it can lead to different crystal structure, lattice structure of the perovskite, which are more stable. So different ways are there to reduce the degradation of the perovskite. One way is to use additives. I mean, use some say organic additive during the synthesis of the perovskite thin films, so which can form cross link between the perovskite grains. Now, to explain this, I will go to the diagram directly. Okay. So here you can see, whenever a perovskite thin film is formed, so this is a cross-sectional representation taken from this publication. So as you can see, this is a transparent conducting oxide, then electron transport layer, and on which a photoactive layer, that is perovskite, is formed. But when a perovskite thin film is formed by different methods, it is a common observation that it is made of different crystallites or different grains. So in cross section, you can see those grains in this way. So it is clearly seen that in some grains, the grain boundaries may be compact, but somewhere you can have a small gap between the two grains, or either you can have a large gap between the two grains. So when you deposit a whole transport layer over the perovskite, then it can form, as it can be clearly seen here, there is a shunt between the whole transport layer and electron transport layer. It is a big shunt, it is a small shunt here. Okay, and therefore if you add some organic additive into it, as it is shown here by this green color, then you can just fill up these grain boundaries, and you can prevent formation of these shunts here, which can definitely improve the structure or the stability of the perovskite films. So formation of the grain during the perovskite film formation can cause its degradation. We can use some organic additives into it, and which can reduce the moisture vulnerabilities at the grain boundary. It can also prevent the path for the moisture to penetrate into the perovskite film, because as we have seen, it is filling up the grain boundaries. Then the additives can also provide some nipplation sites, which can improve the crystalline structure of the perovskite and reduce the penetration probabilities. Okay, so when we prepare thin films of the perovskites as a photoactive layer, then we can add certain additives into it, and it can lead to stable perovskite thin films. Okay, this is one way. Then another way of preventing the degradation is to have encapsulation. It is a very obvious way. You just encapsulate the solar cell with some UV curable epoxy resin, and that will prevent the environmental moisture or oxygen from penetrating into the perovskite layer. So in this way, we can have improvement in its stability. So basically, our work is focused on this topic, that how we can form perovskite thin films with some additives in it. So as I have told you, these additives have a function of preventing the penetration, as you can it can be seen in this figure also. So these are the lines which represent the grain boundaries. So there can be vacancies here, and those can be filled with some other additive, and it can improve the stability. Okay. Secondly, the advantage of having a second component in the perovskite is to have, we can form a bulk heterojunction. This is a typical diagram which shows a bulk heterojunction structure like this. So this is a CH3 NH3 PbI3 is a perovskite. ICBA is some organic fullerene derivative, and it is forming a structure like this. It is called as bulk heterojunction. Now, what is the advantage of having this? Now, this perovskite have the electron and hole mobilities not exactly identical. Okay, so we can have a second component along with the perovskite, so that we can match the electron and hole mobilities. Okay, so with these two objectives, we can have an additive in a perovskite film or a perovskite precursor during the thin film formation. But what is the problem in it? Whenever we add a second component in the same solvent, for example, we wish to form CH3, NH3, PbI3. So we will dissolve the precursor, chemical precursor for this perovskite in some solvent. Now we want to add a second additive in it, say ICBA. It is a name of say organic compound. So we will try to add this ICBA into the same solvent, so that we will have in a single solvent two precursors, two additives, and in a single step synthesis we can form such type of structure. But the problem is that there is a solubility limit of both these components in a single solvent. Okay, so remember, either the perovskite or the second component, they can have various options. Even perovskite can also have different formula. The second component can also have a different chemical option. So having both these components equally soluble in the same solvent may not be possible. Okay, so we focus on this problem, and we find out that we can overcome this problem using a scheme known as surfactant-free microemulsion. Okay, so I will try to finish in the next 10 minutes. A microemulsion is a state which is represented in this diagram. Either we can have oil in water microemulsion like this. I mean, oil phase in water phase, or hydrophobic phase in a hydrophilic medium, or hydrophilic phase in a hydrophobic medium. So this is a typical structure of two solvents is called as microemulsion. It is a homogeneous system consisting of mixture of two or more immiscible liquids. Remember, both these liquids are immiscible, and so they are forming the microstructure, microemulsion. We have formed this microemulsion without use of any surfactant, means without use of any such chemical like this. A surfactant is a chemical which forms a molecular layer on the hydrophobic phase like this. Okay, so that it can form a stable microemulsion. But the presence of these additional molecules like this, that is the surfactant molecules, can be a problematic thing for thin film formation. So therefore we try to avoid the use of the surfactant, and we form the microemulsion using a surfactant-free scheme. Okay, so the microemulsion that we work was this. We use cyclohexane as a solvent for the organic compound, that is ICBA. We use DMSO. This is a solvent that we use as a solvent for perovskite, and we mix acetone in this solvent mixture, which stabilize the microemulsion. So here the acetone is not acting as a surfactant, but it is mixing with the cyclohexane as well as DMSO and stabilizing the microemulsion. So remember, the DMSO is a solvent for perovskite. Cyclohexane is a solvent for second component, that is organic component, and both are immiscible. Okay, so here we can overcome the solubility limit, because DMSO is good solvent for perovskite, cyclohexane is a good solvent for organic component, and so there is no solubility constraint. We can use different solvents together for two different solutes, and we can form a microemulsion out of this. And this microemulsion is then used to form a thin film of perovskite. Now we have observed that this is the ratio of DMSO. X-axis indicates the ratio of DMSO and the cyclohexane. Okay, so if the ratio of DMSO and cyclohexane, that is the two solvents which are forming the microemulsion, if it is changed, then we need different proportion of acetone to stabilize the microemulsion. Okay, for example, if the proportion of DMSO and cyclohexane is 1, that is they are in equal volume, then we need about 45% of acetone to stabilize the microemulsion. Means if the acetone is less than 45%, the microemulsion will be unstable and both these solvents will totally separate away from each other. Okay, and if the acetone volume is greater than 45%, then and then only the two solvents will form a microemulsion state. Okay, so it means that as the proportion of DMSO and cyclohexane changes, we must have a specific acetone percentage to stabilize the microemulsion. If this specific acetone percentage is not present, then the microemulsion will get unstable and DMSO and cyclohexane, both these solvents will form separate layers. Okay, so we use this fact to simulate the variation. See, now I will take 5 minutes to explain what we have done. We know that suppose if I take a microemulsion, okay, with some say DMSO and cyclohexane. In DMSO, I prepared or I put the precursors of perovskite. In cyclohexane, I put precursors of ICBM. Okay, I prepared a microemulsion of this two solvents and use it for the thin film formation. So when this microemulsion is put on a substrate and the substrate is heated, so naturally the DMSO as well as cyclohexane, they start evaporating. And as the evaporation starts, not only both these solvents, it has an additional acetone also. So as we form a, suppose this is a substrate, okay, and on this we deposited a thin liquid film of this microemulsion. So evaporation of the solvents will start, and the evaporation rate of DMSO, the evaporation rate of cyclohexane, evaporation rate of acetone, all are different. So as time passes, the proportion of D, the volume of C and volume of A go on changing with time. Okay, so if you just focus on this diagram, you can see as time passes, the proportion of or the volume of the cyclohexane, the volume of the acetone, the volume of the DMSO, all are changing with time as the thin liquid film evaporates to form a solid film. Now, as the three components changes, naturally the ratio of D and C go on changing with time. And we have seen that the ratio D by C needs a specific volume of acetone to have microemulsion. If this acetone is not available, the microemulsion will get disturbed and it will form separate layers. So here in this graph, we can see that as the time passes, you can focus on this axis, as the time passes, the acetone, which is present during the thin solid film formation, is less than the acetone which is required for microemulsion purpose, okay, to stabilize the microemulsion. And therefore, from this time to this time, this is the situation. The acetone which is present in the liquid is less than the acetone which is essential, that is this one. So during this period, the microemulsion is unstable. But as the time progresses, the ratio of D by C changes, acetone changes, and we can see during this time, the proportion of acetone is sufficient than required. And therefore, during this time, the microemulsion is stable. So you can see this simulation tells that as the thin film is deposited on the substrate and the substrate is heated to form a solid thin film formation, during initial some time period, the microemulsion is unstable. After that, it becomes stable. Okay. And of course, this time period or this time period is a function of how much acetone is added initially for the microemulsion formation. Okay, so we can see that if we increase the proportion of acetone in the microemulsion formation, this time period will decrease. Okay, so in the next slide, I will show you. So if we increase the acetone proportion initially, then this time has been increased, you can see. Now, if we still increase the acetone proportion in the microemulsion initially only, then you can see in this diagram that the emulsion is stable right from the beginning of the solidification up to the complete solidification. Okay, so the important point is that when you form a precursor solution for the deposition of perovskite thin film, we can have specific volume of first solvent DMSO, specific volume of second solvent cyclohexane, and the third solvent acetone. Okay, and depending on the proportion of acetone, we can have different phases of microemulsion, whether it will be stable or unstable. Okay, if it is unstable, for how much time it will be unstable and for how much time it will be stable during the thin film formation, that we can control. And due to this, the nature of the microstructure of the thin film also changes, and the change in microstructure has effect on the optical and electronic properties. So I will directly go to the last result. This is the thin film deposition system, that is a slot die deposition system. It is called as slot die deposition system that we have indigenously fabricated in my laboratory. This system is being used for the fabrication of perovskite thin films for solar cell application. The XY motion of the this slot die head, this is called as slot die head. The XY motion is controlled by Arduino circuit, very simple circuit that my students have fabricated this circuit with the software necessary for it. So with this, we can control the XY motion of this perovskite head, and using this, we can prepare the thin films of the perovskite material. Okay, so as I have told you, this is a photograph of a microemulsion. You can see this is the one phase, and say this is the second phase. Okay, so as the time goes, if you create a thin film of such microemulsion on the substrate, as time passes, okay, the state of the microemulsion go on changing. The microemulsion may become stable, it may become unstable. So if it goes towards instability, these two drops may merge with each other. This may merge each other, and that can form a big drop. Okay, now the first solvent, suppose it contains the perovskite precursor. If this second solvent, these drops, they contain the ICBA precursor. Okay, then just by controlling the size of these droplets during the thin film formation, and we have seen that we can control the size of the droplets during thin film formation by precisely monitoring the acetone content in the microemulsion. So we can control the distribution of this second component in the first component. So you can see here, you can say this is a perovskite crystals. These are the grain boundaries. Okay, and in the grain boundaries, you can form the small crystallites of the second component, ICBA. Okay, so in what way they are distributed here, with what size they are distributed, that we can control by simulating the evaporation dynamics of the microemulsion, as we have seen. So this is how we are trying to fabricate the thin films of perovskite as a photoactive lever. I will directly go to the important result, that just by controlling these parameters, what we have got. So this, you can just focus your attention on say this one. This is a photoluminescence response of the perovskite film that we have formed. It is a perovskite with ICBA. Okay, so here perovskite acts as a donor of charge carriers. ICBA acts as the absorber of the charge carriers. So if the charge transfer from the perovskite to the ICBA is good, then the photoluminescence intensity decreases. Okay, so this figure tells that if you simply take perovskite, then the photoluminescence intensity is high. Okay, but if you prepare a blend of perovskite and ICBA with the method that I have just explained, then there is a significant reduction in the photoluminescence intensity, indicating efficient charge transfer from perovskite to the second phase. And this type of charge transfer is essential. It is needed for efficient photoactive performance of a photoactive layer. So you can see in some other cases, the dip is not much. In some cases, it is even very less. But by carefully controlling the evaporation dynamics, by carefully controlling the proportion of the three solvents, D, C, A, we can control the microstructure, which can give you very good photoactive response. Okay, so this is what we are doing. Of course, this is still in a primary stage. Primary results have been published in the research journal, and more work is being done with some other solvent compositions. We have formed perovskite thin films with some other organic component, and here also it is clearly seen the distribution of the second component at the grain boundaries can be controlled very precisely using the microemulsion scheme. So I hope that I am able to explain what we are doing, starting right from the basic things, so that it is understandable even to the master students. All right. So thanks a lot. I acknowledge the work done by my student, Miss Devasri Opasni, who is an Inspire Fellow of DST. And the work that I have presented here is a contribution by her. So thank you very much.
Sir, thank you. Hello.
Yes, I am getting your voice, please.
Yes, yes. Hello. Just a minute, sir.
Yes, yes, yes.
Okay. Sir, thank you very much. Dr. Jejev Salisa delivered a very good lecture regarding perovskite solar cell, that is PSC. And this PSC is a need, today's need, that is renewable source of energy. As per our need, sir, work on the hot issue, that is the PSC. Now the topic is open for discussion. If you have any query regarding the topic, you can ask. Yes, anyone? Sir, one question, please. Hello.
Yes.
Regarding perovskite solar cell, the material used for PSC, how the stability, we can control the stability of PSC, or on which factor the stability of PSC is dependent?
Yeah, as I have already talked on these topics during my presentation, the stability is affected due to the presence of moisture, then oxygen, and temperature. So there are various ways by which we can make the perovskite stable, and I have talked on this also by using different combination of the cations as well as the halides. We can form different structures, as well as by using some additives. We can control, we can encapsulate the solar cell, and we can stabilize the solar cell. So there are various ways which are possible.
Okay, sir. Okay, thank you. Thank you very much.
Okay. Thank you.
Dr. Salisa delivered a very good and informative lecture on PSC, which is the major potential for future renewable sources of energy and fastest advanced solar energy. Sir, thank you. Thank you very much.
Thanks a lot.
Now, on the behalf of again organizing committee of second international conference on recent advantage in materials science and nanotechnology 2022. In this fourth technical session, the last invited talk will be delivered by Dr. N.L. Tarwar sir. So, I have again opportunity to introduce Dr. Tarwar sir. Dr. N.L. Tarwar sir recently working as an assistant professor in the Department of Physics, Shivaji University, Kolhapur. He joined as a postdoctoral fellow in 2021 to 2014, 2011 to 2014. Then he has worked as an assistant professor and head at Lal Bahadur Shastri College, Sataram. Then he has received Young Scientist Award at Second International Conference on Science and Technology, which was held on at Colombo, Sri Lanka. Again, he has received international recognition in the World Scientist and University ranking in 2020 and 2021. He also received international recognition in top scientist database made by the elsewhere. Then his research interest lies in the area of solar cell, material science, nanotechnology, etc. He has published more than 70 research papers in the international reputed journals, and his citation index is a very good citation index, that is 1896, and H index is 28. He has completed one minor research project funded by Sri Shivaji University Kolhapur. He has awarded by the grant up to 22 lakhs from SERB for the teachers associateship for the research excellence. Then he is a member of BOS for C.K. Thakur Arts, Science and Commerce College, Panvel, which is the autonomous college. He has received 4 Best Paper Award in the national and international conferences. He has a very good academic and research record. Again, he has a very vast biodata. Therefore, due to time constraint, I could not give the details information regarding Dr. Tarwal sir. Again, I would like to invite Dr. Tarwal to deliver his guest lecture, to deliver his invited talk. Sir, please welcome. I get that. I am.
Good evening, all of you. Thank you, Dr. sir, for a nice introduction. First of all, I congratulate GS Tumpe College, Arts, Commerce, Science College, Sandur Bazar, Amravati, for organizing this nice conference with a special theme: recent advances in material science and nanotechnology. In collaboration with the IQAC, Sant Gadge Baba, Amravati University. I also thank for giving me this opportunity, respected Principal Ramteke sir, Wagule sir, convener of this conference, Bijwe sir, Secretary of this conference, Devde Madam, my friend Ashish Rajguru, then co-convener of this conference, Pawar Madam, Bansod Sir, and all the faculty members and my dear students. I am here to deliver my talk on the fabrication and performance of the copper-based chalcogenide solar cell devices. Myself, Dr. Enel Tarwad. I am assistant professor from Department of Physics, Shivaji University, Kolhapur. See, this is my university is here, locating here. See, this is a very green and luscious campus of the Shivaji University. You can visit our Shivaji University anytime. And I am belongs to the Department of Physics. Yeah, see, this is our sun, and we are receiving various radiations from the sun every day, and from that sun we receive the energy that is a very free. We can say it is a free and abundant energy we can receive from the sun, and we can extract this energy in terms of the power. So we can extract that power from the sun. See, this is actually one device. This is a device which converts the solar energy into the electric energy, and see, that device is called as a solar cell. Now I am focusing the solar cell here. I am introducing the solar cell and what is the basic function, principle and working of the solar cell. Now see, this is a picture related to the Parker solar probe. Parker solar probe. See, actually in the space we don't have the energy, electrical energy we don't have in the space. That's why in order to run the satellite as well as the probe like this one, in order to study the sun's exterior, we have to launch some solar probe like this one, Parker solar probe. And in order to smooth their actually working, okay, we need some energy, and that energy that we are taking that energy from the sun, and that devices are called as the solar cells. Therefore, the solar cells are the device which convert the solar energy into the electrical energy, and with that energy we run the satellite as well as the various probes like this one. Okay, next. Yeah, this is my outline of my presentation where I will explain about some research journey, my research journey towards South Korea from Kolhapur, and again back to the Kolhapur from South Korea. And then this is actually some background of the sun. Then I will explain some introduction of the semiconductor. Actually, this is a very important theme and subject to the MS students, where they are studying nowadays the semiconductor. Now again I will explain some principle of the photovoltaic solar cells, means photovoltaic effect, and then generations of the solar cell, then some fabrication process of the solar cell, and finally there is some conclusion and my achievements are there. Next. Yeah, this is my abstract I submitted to this international conference, the entitled Fabrication and Performance of the Copper-Based Chalcogenide Solar Cell Devices. Next. Yeah, this is my Department of Physics, Shivaji University, Kolhapur, where we have we have funded that. Yeah, actually we have funded from various agencies like UGC DRS 1, phase 2, as well as we have our department funded by the ASSIST program, then DSA 1, DSA 2, okay, then DST phase 1 as well as phase 2. Again this year we also sanctioned phase 1, and first sponsored our department is there. Next. Yeah, this is my research journey from Kolhapur to the South Korea for my postdoctoral research fellowship, and again I came to the Kolhapur for my job, assistant professorship. That is direction where the South Korea located in this world map. Next. Yeah, this is our India, and we have located here in Maharashtra, and this is the South Korea, very far from the India. It's almost take 14 to 15 hours in the aeroplane. Next. Yeah, this is actually South Korea. This is the map of South Korea, and this is the upper part is the North Korea, where the capital of the South Korea is here, Seoul, and this is our Gwangju. Gwangju is just like a Kolhapur, very town, very smooth town is there. Next. Yeah, this is a flag of South Korea, and see the independence of the South Korea and India is same. What is the Independence Day? 15 August. The 15 August is the Independence Day of the South Korea as well as our India is same. Next. Next. Let's see the Korean lifestyle. Next. Yeah, these are the very beautiful pictures of the South Korea cities. Next. 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 Yeah, this colorful picture you can see from the South Korea. See the questions of the Korean dresses. Next. Yeah. Now I will explain about some basic about the solar system. See, this is our solar system where the planets are located here. And now we have the Earth, which is our third planet. Okay, and see, this is actually the picture of our Earth is here, and picture of the Sun is here. See what is the difference between the Sun and Earth? See, this is actually the Sun is 109 times larger than the Earth. And see, actually, this is our Earth, and this is Sun. And Sun actually there is some nuclear fusion and fusion reactions are there. Okay, H plus H gives rise to He, and some large amount of energy is liberated from the Sun exterior. See this one in kind of the solar wind, and that solar wind reaches to our Earth surface within 2 to 4 days. And see, this is our Earth magnetic field, and because of this Earth magnetic field, this solar wind repels, and that's why we actually survive. Next. Yeah, see some vital statistics about the Sun. See, this is our the diameter of the Earth is this one, almost 13,000 kilometers, and the diameter of the Sun is just like 1.3439 million kilometers. See, this is actually distance from the Earth is almost 146 million kilometers, and the temperature of the actually this one Sun temperature is actually the mean temperature is just like this one, means the exterior temperature of the exterior of the Sun is just like a 500 degrees Celsius, but at the core you can find very tremendous actually temperature, that is a 15 million degrees Celsius inside the core. Next. Yeah, these are some questions for the student. I just put here some questions. See, how does the mass of the Sun compare to the rest of the all planet system, solar system? See, this one Sun contains almost 99.85%. And see, Sun actually this actually mass of the Sun in the solar system is almost 99.85%, and rest of the 0.15% is just because of all the planets, and 0.15 in that 0.15 our planet, our Earth is also there. Are there the star near to the Earth than the Sun is? Yes, actually there are the back. Yeah. Actually, there are the no closest star. Okay, only Sun is our closest star. That's why we are receiving the energy from the Sun in terms of the visible light, then UV light, and the IR radiation. Does the Sun have the solid liquid interior like the Earth? No. Actually, Sun is composed of the hydrogen and helium. Therefore, Sun is composed of the hot gases like the helium and hydrogen. What is the surface of the Sun like? The Sun has no solid surfaces and no liquid surfaces at everywhere. Okay, the surface we can see which is composed of the hot and churning gases like hydrogen and helium. Does the Sun rotate? The question is, does the Sun rotate? Yes, actually Sun rotates, and the Sun surface rotates differentially once every 35 days near its pole, and once every 25 days near its equator. What makes the Sun shine? The answer of this question is actually because of the thermonuclear fusion reaction, the Sun shine. Next. Yeah, this is actually some radiation we are receiving from the Sun. Actually, we received almost suppose Sun is emitting 100% radiations, but at the surface of the Earth we just received around 47% only, and the rest of this radiation they are just scattered and just transmitted and just back scattered from the atmosphere. And among these 47% of the solar radiations, we have received 2% of UV, and then 47% of visible radiations and 51% of the air radiations we are receiving on the surface of the Earth. See this one, and see next one. Yeah, this is solar map of India, where we can see here the almost the state like Rajasthan that received a large amount the radiation, solar radiation. See, this one is, and after the Rajasthan, actually we the people from the Maharashtra, we are receiving the second number of the radiation from the sun. And see, about the 500 trillion kilowatt hour per year energy is incident over the India's land. Okay, and with most part of the receiving almost the 4 to 7 kilowatt power per square meter per day. Next one. Yeah, these are the some two ways. Means there are the two ways for actually this one is just producing producing the electricity and producing the heat from the solar energy. There are the some two ways, okay, to generate the heat as well as the electricity. There are the two devices, like one device is like thermal solar devices, where actually we are using the air radiations. Means we can convert the solar radiations into the into the heat energy, and that devices are called as thermal solar devices. And another type is just like a photovoltaic solar energy, where we can use the visible radiations, and we have some solar cell devices that convert the solar energy into the electric energy. Next one. Yeah, actually what are the advantages of the solar energy? Because solar energy is a free to all, and then it is abundant, and also it is a clean energy, as well as it's a reliable energy. And what are the disadvantages? There are some many disadvantages, like it is a discontinuous, means it actually we receive the solar radiation only day. At the night we cannot receive the solar radiation, therefore it is called as a discontinuous. And also there are some diffuse radiations are there, and there are some problems in the collection of the solar energy, conversion of the solar energy, and storage of the solar energy. There are the various problems, and because of that there are some disadvantages of the solar energy, and there should be many research have to be research are going on. Now this is just like a atomic structure, and see, this is actually matter which is a consist of the solid, liquid, and gases. Okay, and here the again solid is converted into the, we can say it is a conductor as well as semiconductor and the insulator. Suppose this is we are taking some example of the here atom, where we can see there are some nucleus. We can say it is the core one. Okay, and in the nucleus we can have proton as well as the neutron, and the electrons are just revolving around this nucleus. Okay, this is actually atomic structure of the any element we can see. Now suppose we are taking some example of the zinc oxide. Okay, zinc oxide is semiconductor. Then we have some actually structure like this one. The nucleus is here, and the electrons are moving around this nucleus, and up to which levels the electrons are filling, that is called as a valence band. And the empty bands are nothing but the actually the conduction band. Okay, in terms of the zinc oxide, we have some gap between the this one valence band and the conduction band, and it is around the 3.3 electron volt, and this is called as a band gap energy. Next one. Yeah, actually very simple question. When light falls on the solid, liquid, and actually solid that is conductor, semiconductor, and the insulator, what happens? The light radiations fall on the conductor, semiconductor, and the insulator. This is the answer of this one. When the light fall on the just like a conductor, then what happens? Because of the plasmon, it replaces the light. Okay, and here there is some condition of the semiconductor here. That condition should be the h nu is greater than or equal to Eg. That time we can absorb the energy. Okay, otherwise if that energy is actually the photon energy is higher, okay, we can say higher than or equal to this band gap, that time it absorbs the electron, absorb the photon energy by this electron, and it excites from valence band to the conduction band. Again after some time it just like emit from the conduction band to the valence band. Okay, another question is like this one. When we are taking the example of the insulator here, and what happen? Actually light falls on the insulator. See, the photon energy is very less than the band gap energy that time, and therefore the all radiations we are passing, or we are actually incident on that actually insulator, that all radiation just goes on transmitting. Next. Yeah, and this property we are using in the solar cell, that is the absorption properties of the semiconductor. Okay, and we are using this property in our solar cell. Next one. Yeah, this is a solar cell. Actually, I already mentioned the solar cell is the electrical device which converts the light energy into the electric energy. Next one. Yeah, this is actually a solar cell. That solar cell actually works on the absorption of the actually light, solar light. Then we have to just make the separation of the charge carriers of the opposite type. And third one is that separation of the charge carriers. They just throw into the external circuit. See, this is actually a device of the silicon solar cell device, where we can see there is some N-type silicon is here and P-type silicon is here, and we are making some junction of the P-type silicon and N-type silicon, and at that junction, see, there are some incident of the solar radiation. Then there is formation of the EHP. We can say it's the electron hole pair, and because of the drift-in potential or barrier potential of this junction, that EHP is just like we can say it is breakdown, and the electrons go through the external circuit, and that times we just glow some light. Next one. See, when we are looking the solar cell, we can see only one surface. But when we just have some cross section of the solar cell, see, there are some different layers of the solar cell. Now see, first one is just like a cover glass. Means we are looking our eyes, just a cover glass, and inside that one just transparent adhesive layer is there. Then anti-reflection coating is here. Then the N-type semiconductor, then P-type semiconductor, then some back contact is there. Okay, next. Yeah, actually this is the first generation of the solar cell, which is related to the silicon solar cell. And now see, this one is silicon having the theoretical efficiency around the 34%. And silicon solar cell means it's just like making the actually junction between the N-type silicon and the P-type silicon. I will explain later on. And see, there are some, even though there is theoretical efficiency around the 34%, but we cannot get this efficiency at the lab scale. Okay, because we are getting some almost half of this one. Okay, means we are taking some silicon crystal of the silicon, then we are getting some 16 to 19% of the efficiency, and we are just making the some multi-junction solar multi-crystal or polycrystalline silicon solar cell. That time we are getting the 14 to 15% efficiency. Next one. Yeah, this one is a silicon. Silicon is actually which is in the fourth A group, and that have some four electrons in their outermost orbit. Okay, when another silicon comes together, that time it gives the 4 electrons to the next silicon, and then they just share the electrons. Okay, and this is called as the covalent bond. And because of the making the covalent bond together, actually the silicon network is happening. Okay, and when actually this is silicon is a pure semiconductor. Okay, we can say it is an intrinsic semiconductor. That's why it will not actually conduct. Okay, but if we just dope, actually this is having the 4 electrons. If you dope the trivalent impurities here, then actually whole creation is there. And when we dope the pentavalent impurity from this one, then we are creating the electrons. Okay, and that actually when we dope the trivalent impurity, we can say it is actually P-type semiconductor, and when we dope the pentavalent, it is called as the N-type semiconductor. Next one. Yeah, this is a process of the making this actually silicon ingot. Means the SiO2 means the silica or SiO2, the silicon chunks are just heated in at the temperature of the 1800 degrees Celsius, and this is which we can say it is a molten silicon. Okay, and when we are just giving some actually putting some actually silicon actually seed is here, and then that silicon seed just we are actually taking up with the help of the pulley, and that time we are making some just like a silicon ingot. Okay, and this silicon ingot is a pure one. Okay, and after the laser technology, or by using the laser technology, we are cutting this silicon ingot in the silicon vapors. Okay, it is just like a vapors means they are just like a thin slices. Okay, next one. Actually this one is pure one. And next. Yeah, actually the silicon solar cell technology is related to the actually 3-1. Means one is the single silicon crystal, single silicon, then polycrystalline, and third one is the amorphous silicon. Okay, next one. Yeah, actually solar cell that made up of from the polysilicon, and they look like the blue color. Okay, and the efficiency of that one is around 14 to 16%. Next one. Suppose they are making from the mono, means single silicon crystal, they are look like the black color. Next one. And then the amorphous silicon is there, it looks like the blackish transparent. Next one. Yeah, This is a difference between the actually polysilicon panels, monosilicon panels, and the thin film actually panel. See, this is actually efficiency of the devices. Even though efficiency is high for the monosilicon panels, but the cost is also high. Okay, therefore we are going for the actually thin film solar cell, even though our cost is very low. Next one. Now this is a doping process where we can dope the semiconductor, either it is a p-type or n-type. Now this is a doping process, means doping means just like a replacement of the small number of atoms, okay, in the lattice by atoms of the neighboring columns. Next one. Yeah. See, this is actually our intrinsic semiconductor where we have some network of the silicon. Okay. But when we dope some pentavalent impurity like this one, means we can say phosphorus, okay, antimony, that time there is extra electron is here. Suppose here we have some 4 electrons and extra means 5 electrons are there. Means actually 4 electrons are actually they are just shared with the 4 electrons from the antimony or arsenic, and that time one extra electron is remaining, means that extra electrons means we have some n-type conductivity, okay. And here next back. Yeah, here the exchange is p-type semiconductor, means we have some dope trivalent impurity. Trivalent impurity means like a gallium, okay, gallium, aluminum. That trivalent impurity having the 3 electrons in their outermost orbit, and they actually silicon having the 4 electrons. The 3 electrons shared with the 3. Actually, one actually electron is actually we required here for sharing of this electron from the silicon, but there is no electron, okay. That is nothing but the hole, means there are the creation of the holes when you dope that actually trivalent impurity into the silicon. Now the energy levels also shifts, okay. For the intrinsic semiconductor, the energy levels are the middle one here, and when we dope the just like n-type semiconductor, that time the Fermi level goes to the upper direction, okay. That is up to the toward the conduction band. And when that is a p-type semiconductor, the Fermi level shifts down here near to the valence band. Next one. Yeah, the types of the semiconductor. The semiconductors are the we can say it is either an intrinsic semiconductor or it is an extrinsic semiconductor. Again, extrinsic semiconductor is again 2 types, n-type and p-type. In the extrinsic semiconductor, n-type semiconductor, we have some more electrons, means majority charge carriers are the electrons, and here the majority charge carrier are the electron here. And here there are some other actually band gap semiconductors, means one is the direct band gap semiconductor and another is the indirect band gap semiconductor. And direct band gap semiconductor, we have the EK curve, okay, means the valence band and the conduction band are the same K values. Here in the indirect band gap semiconductor, the EK curve means the valence band and the conduction band are not in the same K values, they are in the different, okay. That's why there is some no energy loss is here, but here there are some loss, because when the light fall on this actually valence band or that material, then the electrons from the valence band that takes the actually the photon energy and get excited from this to this one, and again after some time it emits like this way, okay. Excitation and emission is just like one way, but here when that actually in the indirect semiconductor like silicon, okay, that time the solar radiation fall on here, that electron gets the energy from the photon and it excited from this to this way, and after this one it goes like this way here, okay. There is some, we can say, phonon or lattice vibrations are there, means some energy is lost, okay, in terms of the indirect band gap semiconductor, and that's why the silicon having the less efficiency, okay. And here the cost is also silicon production cost and the silicon fabrication solar cell is also high. Next one. Actually, this is the impact of band gap semiconductor in on the efficiency. See, this one is silicon having the band gap is around 1.1 electron volt, okay, and it shows highest efficiency, even though there are some other band gap materials are there which shows some less efficiency. Next. Yeah, creating PN junction is a very important task here. That's why we are just making the n-type semiconductor and p-type semiconductor, and they just coming together in order to sandwich that n-type and p-type semiconductor here. And when they are just coming together, then this is called as an unbiased condition. And an unbiased condition means what happen actually, here there are the p-type semiconductor having the number of holes, and this is actually n-type semiconductor having the number of electrons here. And then when these two actually semiconductors comes together, there is formation of the battery, or we can say it is a reverse battery, or we can say it is a potential barrier, and it is having some 0.7 volt for the silicon. Now when we are just applying this actually forward bias, mean what happens, positive is given to the positive and negative n type semiconductor is given to the negative here. Okay, this is called as the forward bias. And when it is opposed, like a p type semiconductor is connected to the negative terminal and n type semiconductor is connected to the positive terminal, that time actually the depletion layer is here, that actually disappears here, means it becomes very low, or in here the depletion becomes larger. Okay, and because of this one, the electrons are moving in this direction only, in this forward. Next year. Next year, sir. Next year. Actually, this is the world record efficiency of the silicon here. See, this one is the efficiency of the silicon at the lab. We can assume that is almost 24% here, but it is not possible at the practical level. It is almost 12%. Okay, and see, this is actually when we plot the IV characteristic of the silicon or any solar cell device, it looks like this one. Okay, the I is here, I means current is here, and voltage is here. And for the ideal solar cell, it shows the curve of the IV characteristic is just like a rectangular curve. Okay, and for that one we have the fill factor value is 1. Okay, and actually the fill factor means there are some loss of the power. Okay, that's why it goes like this one, and we get a knee-like curve like this one, and that time the fill factor is less than the 1. Okay, and see, this is equivalent circuit of the solar cell. We have that time the two resistance, one is the RS and another resistance is the RSS, that is shunt resistance. Ideally the value of the RS for solar cell, ideal solar cell, it is 0. Okay, and for the shunt resistance, the value is of the shunt resistance, it is infinity for the ideal solar cell. Next one, sir. Actually, this is some efficiency of the word efficiency. See, these are some efficiencies started from the 5% here, and see then that efficiency goes like this one. Okay, this is an increasing trend like this one, and that efficiency chart is given by the NREL, one of the famous actually solar cell energy research actually institute in the US. And see that there is some highest efficiency, that is the 43.5%. This is for the multi-junction solar cell. Okay, next one. Yeah, these are the actually what parameters actually gives the ideal solar cell. See this one, the material having some direct band gap structure. I already explained this one. Then actually what happens, because it shows some same K. Okay, that's why there is no energy loss. Therefore, we need some direct band gap semiconductor. Okay, another one is the band gap of our material is actually in the range of 1.5, 1.2 to 1.6 electron volt, and then it should be some actually non-toxic materials, and then it is a reproducible deposition techniques. Okay, we need this one, and it is suitable for the large area deposition. And finally, we have some long-term stability of that material. Now, the what is meant by the photovoltaic means, actually photo means light, okay, and voltaic means the electricity. Then we have to convert the light into the electricity, means it is called as a by using the photovoltaic effect, okay. And see that there are some formulae in order to calculate the fill factor as well as the efficiency by using this formula. Next one. Actually, I am explaining the second generation solar cell, which is related to the thin film, and I am taking some example of the CIGS. Okay, CIGS means copper, indium, gallium, selenide. Okay, and this is the solar cell device of the CIGS. बंद है लाइट बंद करते हैं हाँ लाइट बंद करते हैं राव दे हाँ थोड़े से देखिए अर्धे दे अर्धे दे अर्धे अर्धे दे अर्धे थैंक यू Actually, the CIGS is a direct band gap semiconductor having the world record efficiency around the 22% or 20%, okay, which is already demonstrated here. Next one. Yeah. Actually, there are some other techniques also. We can deposit the direct semiconductor like spray pyrolysis there, okay. And another technique is the PSPT, means pulse spray pyrolysis technique, okay. Because these are some simple techniques, spray pyrolysis technique, which is a very simple and inexpensive chemical deposition technique. From that technique, we can easily deposit the direct band gap semiconductors. Next one. Yeah, other technique like a electrode deposition, we can use the electrode deposition for the deposition of the CIGS as well as the CZTS solar cell or other direct semiconductor. Also, there is another technique, that is deep coating technique, or we can say soldier technique is also there. Next one. Yeah, the question is why CZTS? Actually, the CZTS is a quaternary semiconductor having the component like copper is there, zinc is there, tin is there, and sulfur is there. Instead of sulfur, we can use the selenide. Okay, and this is a new PV material and promising material having the energy band gap energy that lies between the 1.44. Actually, when we just already mentioned, there is some graph of the solar radiation, like solar spectrum is there, means high energy is just like a top one. Okay, the the top material receiving the more and more solar radiation, and that having the band gap 1.45. Okay, if your material having the band gap 1.45, that means your material absorb more and more solar radiation. That's why the CZTS as well as the CIGS materials and kind of this one means CFTS is there, CZTS is there, CMNTS is there, CMGTS is there. There are the various materials that absorb the more and more solar radiations, and also we can get the almost in our lab we can find almost efficiency is greater than the 10. Next one. Yeah, this is a technique I use for the deposition of the CZTS. The electrode deposition I use for the synthesis of the CZT precursor. CZT means copper, gas, zinc, and tin. Okay, we can use directly. Means one step deposition technique is there. Means you can take the copper, zinc, and tin in a one bath and give some potential. Then at a time you can deposit the CZT. Otherwise, there is another method like you can take copper is there, zinc is there, and tin is there. Means you can take layer by layer deposition, and after that you just anneal this one. Okay, means that setup is called the sulfurization setup, and another setup is the selenization setup. Means this is actually setup having the sulfur inside here. Sulfur powder is there, and here the selenium selenium powder is inside here. Okay, at temperature of the 580 degrees Celsius, that sulfur is diffused in that CZT precursor, and then we can get the CZTS as well as the CZTSC. Okay, and that is actually PV material. Next one. Next. Yeah, these are some characterization techniques I use for characterize my material. That is XRD for phase formation. SEM is for the morphology investigation. Then cross section SEM in order to study the thickness of the material. See, the thickness is very important in the solar cell. Okay, that's why our thickness is just like having that optimum thickness is just like 1.5 to 2 micrometer. Okay, we need this one. And then another technique, that is XPS, we use in order to study the elemental or composition analysis. Then Raman is also important for the chalcogenate or castrate phase detection. And finally, there is some solar cell properties, that is we need some solar simulator in order to study the IV measurement. Next one. Yeah, this is the XRD patterns. See, this one is the XRD patterns. We use the moly substrate. That's why the actually high intensity is related to the moly, and this is actually 112 is phase. This belongs to the actually castrate phase of the CZTS, and that sample are surprised at the 550 for 10 minutes. Okay, and see there are some surface morphology of this one and cross section morphology, cross section of the CZTS device that having the thickness 2.9 micrometer. And see that actually CZT, okay, CZT yes, also that CZTS elemental analysis was detected or was done by the EDX. Okay, next one. Yeah, also we use some Raman technique and as well as the XPS technique in order to detect the elemental analysis here. And see, this one is the Raman of the CZTS, where you can find the various three peaks belong to the CZTS from the Raman spectra, and here from the XPS we can easily detect the CZTS. Next one. Also, we made some solid state device of the CZTS. Okay, see this. What is actually structure of the CZTS solar cell here? See, this is actually our moly is here. Okay, glass is here. After that, moly is deposited on the glass. Yes, finish, sir. And this is the moly, and after that there is some CZTS precursor here, and then there is some very small actually CDS layer is there, 70 nanometer, that is deposited by the chemical part deposition, and there after that there is some zinc oxide nanorods are there that are deposited by the cooperation method, and after that there is some contact. Okay, and actually we received actually we obtained that efficiency of the CZTS solar cell and shown in here. Okay, shown in here these figures. Next one. Yeah, same baseline we use for the CIGS solar cell. Means the actually device structure is here. Okay, and we use the we deposited the CIGS by the cooperation method, and then CDS by the CBD, and then zinc oxide by sputtering, and finally the contacts are taken by the e-beam evaporation. Next one. Yeah, and this is our world record efficiency, having the 19.5% efficiency, and this is our 5x5 solar cell, and this is our 10x10 large area deposition of the CIGS solar cell, and this is the structure of the solar cell, and we almost reached to the 19.5%. Next one. Yeah, this is my conclusion of my today's talk. Actually, detailed fabrication process of the silicon solar cell is explained here, and some physics behind the solar cell, which is given here. Okay, and case studies, I taken the silicon as well as the CZTS and CIGS. I took here as a case studies, and that solar cells based on these devices are demonstrated. Next one. Actually, this is my group from the GIST, South Korea. This is my mentor, and these are some group. And see, there are some building called as a RISE building, where the 4 Nobel laureates are working here. Next one. Yeah, this is Professor Sumio Ijima is here, who is actually discoverer of the CNT. Actually, we met actually at a conference of in the South Korea, and this is actually Alan Higer is here. Alan Higer actually who received the Nobel Prize for the plastic conducting polymer. Okay, and he's also working in our lab in our building. Another scientist, that is Peter Gunberg, is here. He's from the Germany and he's from the USA. He's also working in the nanomaterials. The giant magnetic resistance was his actually main research field. Actually, he died in May. And there are some our actually boss in the electro deposition, that is Bhattacharya, is there, and Professor A.N. Tiwari is from the IMPA, Switzerland, where my friend is actually working. Another is also working. Next one. Actually, this is my research output. Next. Actually, this I just published various papers in international journals. The count is almost 70 papers. Next one. Actually, what gives me the research? Okay, research gives me a lot. Means citation as well as the H index, ITIN index, more than this one. Okay. Also, I received one award, that is the Tare award from the DSC Serb. Also, I received 2 times young scientist award. Next one. Yeah, these are some paper clip. Next. Yeah, this is my strong collaborator from Germany, South Korea, then Australia, then NCL Pune, then Solapur also there. Next one. Yeah, I acknowledge my 2 professors, one my PhD professor, that is PS Patil sir, and my actually postdoc supervisor, Professor Jejev Salisa. Thank you, one and all. Next. Next. Yeah, thank you. If there are questions, welcome.
On application of opposite satellite semiconductor copper extend photo electron properties copper thank you.
Thank you, sir.
Now the topic is for any question. Sir, from my side.
Yeah. Decrease. Yeah. Actually, for band gap, sir. Actually, band gap is the intrinsic property of the material. It cannot vary. Okay, but we are just giving some doping. If you dope that material, if your band gap having the less than 1.45, then you just decrease that material. Okay, this you can just decrease or increase up to 1.45, and our optimum band gap is 1.45 for receiving the more and more light. Then we use some doping. Yeah.
Finally, I would like to thank the command committee for yes, okay, I can see and the organizing committee invite you and you have an opportunity as a member of both technical session of Senate conference. Thank you very much, sir. And now I declare that the both technical session closed.
Thank you very much, sir. I request to all oral presentation participants, please submit your presentation to technical team. I request to all oral presentation participants, session 2, submit your presentation to technical team. Respected humanities on the dais and equally learned participant of the dais. Today we have enjoyed great kind of academic feast, and now we are in the concluding part of the session. I am feeling a kind of honored since I have been assigned the duty of extending vote of thanks towards all dignitaries present here. Honorable Chairperson of the session, Dr. Gopal Dhokne sir, has not only president over the session, but put forward his academics and research finding also. He has obliged all of us, and hence I extend my sincere thanks towards him. We have another guest of the equal stature, and he is Honorable Dr. Jejev Salisa, Head of the Department of Physics, KBC, North University, Jalgaon. Respected Salisa, Respected Salisa has addressed us in this occasion, and this makes me extend my thanks towards him. Yet another dignitary, Honorable Dr. Luca Pellegrino, from CNR SPIN, Genoa, Italy, has also shared his valuable time with us and commented on the emerging trends of the concerned subject, and hence I extend my thanks towards him as well. Honorable Dr. Nilesh Tarwar sir from Shivaji University, Kolhapur, has also addressed us, and by doing so, he has obliged us, and that becomes obligatory to be thankful to him. At last, I extend my sincere thanks towards all learned participants, and with the kind permission of the chairperson, I declare that the present session is over. Now, we start a next session of oral presentation of session 2. The jury member for this session, Dr. Gopal Dhokne sir and Nilesh Talwar sir. I welcome with kind. नाव काय राहू द्या मी वाचतोच ना मग एक नाव आता राहू द्या. The jury member for this oral presentation, Dr. Gopal Dhokne sir and Nilesh Talwar sir. Online. Our first oral presentation is Sonu Patwa, which is online mode. I request to technical team. His title of paper is Analysis of Structure and Surface Morphology, Synthesis of Nickel Oxide Nanoparticles by Hydrothermal Method. He is mechanical engineering student from Veer Bahadur Singh Purvanchal University, Janpur, Uttar Pradesh. Our next oral presentation participant, Harshan Yadav, which is also in online mode. I request Harshan Yadav, please start your presentation. I know. Harshan Yadav. Harshan Yadav. Harshan Yadav. Last 35 number. Last 35 number. OP 35. Harshan Yadav, I need. I request our next participant, Shakti Yadav. OP 24. Hello.
Good evening, all of you. Myself, Shakti Yadav, research scholar under the supervision of Dr. Girdhar Mishra sir in the Department of Physics, Professor Rajan Singh Rajju Bhaiya Institute of Physical Sciences, Veer Bahadur Singh, Purvanchal University. Here I am going to present my work entitled as Theoretical Investigation of Mechanical and Thermophysical Properties of 5D Transition Metal Mononitrides. This is outline of my work, which comprises of abstract, introduction, theoretical approach followed, second order elastic constant and third order elastic constants, and mechanical constant, ultrasonic velocity, thermal properties, ultrasonic attenuation, and conclusions. This is abstract of my work. For the transition metal mononitrides, we have evaluated the second order and third order elastic constant, and with the help of the evaluated second order and third order elastic constant, further I have evaluated mechanical constant and thermal properties of chosen material, tantalum and lanthanum nitride. The transition metal nitride have attracted considerable attention due to their excellent properties, including high hardness, high melting point, low compressibility, and high thermal and chemical stabilities. In this slide, I have presented the theoretical approach followed by me for the study of ultrasonic and thermophysical properties. First of all, we applied the deforming force in the form of varying temperature. Then, after application of deforming force, evaluation of higher order elastic constant has been performed, and with the computed value of elastic constant, the mechanical and thermal properties of the specimen has been computed. Further, the specific heat and thermal conductivity evaluated, and the evaluated value of thermal conductivity and specific heat has been used to compute the ultrasonic attenuation. And when the temperature is varied on a specimen, then the lattice expand and discontinuity arises in the lattice, which gives the change in properties of material. The three crystallographic direction 100, 110, and 111 has been considered. The second order elastic constant and third order elastic constant has been evaluated at room temperature plus varying the temperature. When we vary the temperature, then vibrational part of elastic energy density contribute. In this slide, the formula used for the evaluation of higher order elastic constant has been presented, and the Born-Mayer interatomic ionic potential model is used for the evaluation of the higher order elastic constant. The computed value of second order elastic constant for lanthanum nitride and tantalum nitride has been tabulated here in this slide. And further, with the help of the computed value of elastic constant, bulk modulus, shear modulus, Young modulus has been evaluated using these expressions. Poisson's ratio, Jenner anisotropic factor has also been evaluated using these relations. And the computed value of elastic constant fulfill the Born stability criteria given by these relations, and hence our chosen material is mechanically stable. Further, in this plot, I have plotted the value of bulk modulus, shear modulus, and Young modulus. From this graph, it is clear that for the Young's modulus of tantalum nitride is greater than Young's modulus of lanthanum nitride. It implies that tantalum nitride is stiffer than lanthanum nitride, and in this slide, the formulation related to the ultrasonic velocities for longitudinal wave and shear mode has been given. Debye average velocity Vd has been computed with the value of VL, Vs with the help of these relations in direction 100 and 111 direction, while in the direction 110, the formula for Debye average velocity is this. Debye temperature has been evaluated using this expression. And the plot of Debye average velocity has been shown in this figure. The thermal conductivity has been evaluated using the formula suggested by Morelli and Slack, and the plot of thermal conductivity has been shown in this figure. The specific heat and thermal energy density has been evaluated using the integral involved in the Debye theory of specific heat, and the obtained value of specific heat and thermal energy density are in good agreement with the values obtained by theta d by T table of AIP handbook. From the plot, it is clear that at a higher temperature, the specific heat tends to a constant value, hence obeys the Dulong-Petit law. And while the internal thermal energy increases with the increase in temperature. Ultrasonic attenuation. As we know, when an ultrasonic wave propagates in a medium, then energy loss takes place, and the energy loss, the phenomena of energy loss is termed as ultrasonic attenuation. There are various factors responsible for the ultrasonic attenuation. Few of them are electron-phonon interaction, phonon-phonon interaction, thermoelastic relaxation, and grain boundary loss. And the formula related for the evaluation of acoustic, for the evaluation of thermoelastic loss and phonon-phonon loss is given here. With the help of Mason-Bateman theory, we evaluate the loss. And in the slide, the attenuation, total ultrasonic attenuation have been plotted with a varying temperature, and it is clear that thermoelastic loss is very small in comparison to the Acquisition loss. Therefore, ultrasonic attenuation is predominant due to phonon-phonon interaction. And I conclude that using with two basic parameters, lattice parameter and hardness parameter, second order and third order elastic constants can be evaluated between the temperature and 100 Kelvin to 500 Kelvin, and thermal conductivity is maximum in 111 direction. Obtained result provide better understanding of the elastic and thermophysical properties of transition metal mononitrides. I am thankful to CSIR for providing financial assistance, and also thankful to my lab member for creating a friendly atmosphere at the workplace. Yes, using the approach given by Morelli and Slade, in the slide it is given. Slide. Yeah. Yes, sir. This is formula used to evaluate. In one direction and yes, sir. Thermal conductivity is also depend on ultrasonic Grunwald parameter, and for different direction ultrasonic Grunwald parameter value is different. Hence, we find different value in different direction, and for one direction the value is maximum. Thank you, sir.
I request to all participants. There are 5 minutes for your presentation and 2 minutes for. I repeat, again request all participants. There are 5 minutes for the presentation and 2 minutes for discussion. Next participant is Mr. Sheikh. Sir, 2020.
Hello. Hello. One again.
respected jury, my teachers, and my friends. Good evening to all of you. My name is Akshay Jawaran Panta Gathod. I am from Geology Department, GS Tumpe Art, Commerce and Science College, Tandur Bazar. My topic of paper is morphometric analysis using remote sensing and GIS of Bairamka Sand River, that is the Pili River basin of Amravati district. Next. That is the area of study, my area of study. The area is located in the Maharashtra, that is Amravati district, and the area is given in the maps. Next. That is the study details about the study area. The study area is falls in Geological Survey India proposite number 55G/11 and 55G/12. That is the two toposheets where under which my area is covered. Then the second is the latitude and longitude of the area, basin area of watershed. Then this data which is I have morphometrically analyzed and GIS with the using of GIS interpreted, that is ArcGIS is the 9.3 software is used for the interpretation of data. The study area is near about 193 square kilometers. That is the geological map of the study area, which shows this geological map is prepared by using remote sensing technique and the GIS 9.3 version technique interpreted this, and this map shows the northern part of the map shows the Melghat forest, and as we comes towards the south, the sedimentary rocks and the metamorphic sedimentary and igneous rocks are mainly present in the area. And in the southern part of the area, the massive basalt and the hard and compact basalt is present, which is the Deccan lava flow of Eocene age, Cretaceous to Eocene age. Next one. That is the geology and stratigraphy of the area. The area is mainly characterized by Deccan traps and alluvial. Deccan trap is the basic lava flows on which the area is by which the area is covered, and the age of this lava flows is upper Cretaceous to lower Eocene age of geology. That is the geological age of the basic lava flows of that during that time. And second one is the alluvial formation, that is the mainly sedimentary formations present in the area, and which sedimentary formation is totally related with the Purna alluvial. My river basin is one of the tributary of Purna alluvial, Chandrabhaga and Purna river basin. Next one. Stratigraphy. Previous. That is the stratigraphical succession of the area. The succession is started from the Proterozoic age to the Quaternary age, and in between as we discussed in the geology, stratigraphy and the stratigraphy, we can show that the unconformity is present, and this unconformity divides two types of rock types in the area, and disconformity divides the same rock type but the parallel edges of the parallel rock types of the area. Disconformity means the time gap where there is no deposition, but the rock type will continue same after the discontinuity time period. And the unconformity is the time gap where there is no deposition. As we can see, quartzo-feldspathic gneisses from the Proterozoic age and the upper Gondwana rocks from the upper Cretaceous age is derived from the differentiate from unconformity. Next one. That is the geological map area. Geological map shows the physical features of the study area, and it shows this small dot shows the water bodies, rivers, my river and its tributaries attached to the rivers, and that is the end part of the area. The villages are marked by the conical shape. Near about 27 villages comes under the basin of river basin of the Pili river basin. And that is the next part of the study, drainage map of the area. The drainage shows fifth order drainage, and there are the linear aspects of the morphometric analysis, that is the stream order, number of segments, bifurcation ratio, and stream length. All these are the linear aspects of the study area, which are calculated from the software under the head of morphometric analysis. Next. And that is the aerial aspects of the morphometric analysis, starting from the area, that is 193 square kilometer, and perimeter, that is the horizontal propagation on of the land where the area comes under. Drainage density, it is calculated at is the 2.33, stream frequency, texture ratio, circularity ratio. There is the one term bifurcation ratio, which shows the elongation of the basin, and the constant channel maintenance, that is the 0.04, which is very low in the order. That is depend on the drainage density of the area, and drainage density is calculated by number of streams of all order divided by its area. It is the ratio of, and that is the conclusion from my study paper. Morphometric analysis, which is help us to calculate the linear aspects, aerial aspects, and the relief aspects of the watershed, which can be further used as the development of watershed basin, development of watershed project. And second one is the morphometric analysis is play a significant role to understand hydrogeological characteristics of drainage basin, and the bifurcation ratio shows the natural drainage, homogeneous rocks is present continuously. And the last point is the drainage pattern of this area, which is because of the geology of the area, and that is dendritic to subdendritic. Thank you. Next. Thank you.
Hello.
The drainage graph shows the stream orders by using the ArcGIS software 9.3 version. The data is collected using the remote sensing techniques and interpreted in the GIS software. Thank you, sir.
I request the next participant, Ms. NG English. OP29.
नको यूज नाही त्याचा. Good evening, everyone. Firstly, I would like to introduce myself. I am Nisha Chandrasekhar Ingre, representing GS Tompe College, Chandur Bazar. Next. The topic of my presentation is the green synthesis and characterization of copper oxide nanoparticle using Picus Panda. Next. And these are the authors and our guides. There are various methods for the synthesis of nanoparticles using for the nanotechnology, such as physical, chemical, biological. Among all these, the green synthesis is the most efficient, cost-effective, and very nature-friendly method, because it includes the uses of various quantities, the particular varieties of crops, trees, and vegetable waste, and onion peels, etc., instead of using the toxic or hazardous chemicals. And that's why the green synthesis is the nature friendly and the cheaper method to perform. Green synthesis for the synthesis of nanoparticles is the most efficient method because it can be done in any simple library without much expenses, and it also don't need high quantity of temperature, heat, energy, electricity, or a man work. So what is nanoparticle first? According to the standard definition, nanoparticles are the material whose size ranges in between 1 to 100 nanometers. And as knowing all the applications of nanoparticles in various faculties in various areas, like in medical science, healthcare, cosmetics, electricity, electronics, automobiles, and also in environmental management. Its synthesis is on working, and scientists are also further researching for the different method for its synthesis. Next. So how can we synthesize first the green extract? So as I say, the particular varieties of crops and trees can be used here, which includes neem fruit, and ficus panda, henna, etc. Among all these, we use here ficus panda. So how can we synthesize now it? Firstly, we have to collect ficus panda leaves, which are easily available in our surrounding. Then we have to wash it thoroughly, firstly with tap water and then with distilled water to avoid impurities. After that, we have to cut it into pieces and measure 25 gram of ficus panda leaves. And then, on the other hand, we have to take 250 ml of distilled water in a beaker and add that 25 gram of ficus panda leaves in it. Then we have to keep it on burner for heating. After nearly 1 hour, we have to heat it on the at the temperature of average 70 to 80 degrees centigrade. After further heating it, after 1 hour, it color will change into dark green, and when it color will convert completely in dark green. We have to keep it aside for cooling. After cooling it, we have to filter it with using filter paper. When we filter it, all the heterogeneous mixture of ficus panda leaves and that water gets separated. We have to draw out that ficus panda leaves on it, and the remaining solution, what will be remain in this beaker, is our green extract. Next, then synthesis of copper acetate solution. Simply, we just have to take 250 ml of water, distilled water in a beaker, and add 5 gram of copper acetate, which is in powder form. We have to add it together, and this is our copper acetate solution. Next, the main part of our project is synthesis of copper oxide nanoparticle. For this, we have now green extract and copper acetate solution. We have to take 150 ml of green extract and add 50 ml of copper acetate solution in it by dropping method. After completion of the dropping method, the precipitate will form inside that beaker, and we can appear it forming and settling down at the bottom of the beaker. Then after complete formation of precipitate, we have to again filter it with using filter paper, and then it takes nearly a day for complete filtration, and the precipitate will settle on that filter paper. Okay, we have to remove it, take it aside for drying. When this precipitate will complete dried, then we have to collect it in a china dish, and then we have to crush it into a form of fine powder, and then we have to collect it in a sample bottle. This is our final product, which is copper oxide. Next, result and previous file. After getting the final product, we send it for characterization. Then we come to know that the wavelength of copper oxide, which is the wavelength of our product, is ranges in between 200 to 800 nanometer, and its highest peak is shown at 241 nanometer. Next. After performing this all experiment, we concluded that the green synthesis is the most efficient method and most convincing method, as it also don't need more time. It is also it reduces the risk of environmental pollution. It reduces the risk of contamination, and so on. Next. These are all the references. Next. As we youth are the future of our planet, we have to we must be aware and awaken towards our nature, towards our responsibilities. Okay, so we have to enrich our knowledge, and also we have to enhance the prosperity of our nations, keep promoting towards our responsibilities towards our nature, and we have to be polite and grateful to our nature, and also we have to keep promoting such nature friendly and environmental inventions that's such like green synthesis. Thank you. Yes. What's that? According to its size, when we analyze it, characterize it using UV VIS spectrography, its size. UV spectra, the graph was there, and yeah. What's that? Yes, UV graph. This is the graph, but it's not clear. I don't know why. But yes, so this is the highest peak, and that our result come to us. That's what all. Sir, its length and breadth is size. What's um, I don't know. Sir, on y-axis this is length, axis this is length, length in nanometer. Yeah, it is denoted there also. So we have to draw its band gap using copper oxide nanoparticle, metal nanoparticle, metal oxide. Sir, that green synthesis of copper and characterization of its average range size of copper oxide nanoparticle is 1.2 electron volt. And when we, according to this graph and highest peak, we have to calculate it using formula. And then we come to know its size is 1.2, it is nearly 1.2 or something that, then it's conformly the copper oxide nanoparticle. So it is 1.2 electron volt, 2 electron volt. Its wavelength we found it ranges in between 200 to 800 nanometer, and highest peak, as I said, is 241 nanometer. So we referred many papers for this, and this is a very I think not a new technique. It's very I think the new thing is that we searches for very papers, and we found various examples of it, like using some using neem products and Lawsonia inermis, but because no one uses thicker panda still. I think
SPDC.
Hello. Good evening, everyone. Myself, Shantanu Pramodrao Deshmukh. I am student in GS Tompe College, MSc Physics, second year. Today we talk about the green synthesis and characterization of magnesium oxide nanoparticles by using green neem leaves. Next slide. First one to prepare a metal oxide nanoparticles is basically three methods. First one is physical method, second one is chemical method, and third one is biological method. To present work focus on synthesis of magnesium oxide nanoparticles by using green synthesis method. First one is green synthesis method is a eco-friendly, non-toxic method and low-cost method. The green synthesis method is a bottom-up approach. Is similar to the chemical reduction. In chemical method, to use the expensive chemicals is replace the natural extract such as roots, leaves, kitchen waste, eggshells, and something we use to nature. The synthesis of magnesium oxide nanoparticles and characterization to use the UV spectrum and XRD diffraction method. XRD is used to what is crystalline size, and UV is used to absorption pattern. Next slide, please. Next slide. This is the material metallurgy. Today we focused the work is synthesis and characterization of magnesium oxide nanoparticles to use green synthesis method. Next slide. First one, preparation of neem leaves extract. To prepare the neem leaves extract, to collect the first one to collect the 20 gram of neem leaves is freshly healthy, washed by running tap water 2-3 times, and again washed is used the distilled water. We used to distill water and dry at room temperature 20 to 30 minutes. Avoid the loose impurity. Second one, as the extract solution was prepared by boiling direct leaves in 500 ml beaker and 20 ml of distilled water, and add the 20 gram of neem leaves and heating 100 degrees Celsius from 1 hour. After 1 hour, the cooling down the solution to filter by using the filter paper. Next one. Synthesis of magnesium oxide nanoparticles. The synthesis of magnesium oxide nanoparticles by using 20 ml of fresh neem leaves extract and 80 ml of distilled water was added 500 ml beaker to heated 60 degrees Celsius. 60 degrees Celsius. After some time, 20 gram of magnesium nitrate was add the solution and heating 80 degrees Celsius. 80 degrees Celsius in 4 hours by using the continuous stirrer and hot plate. The formation of magnesium oxide nanoparticles have been observed by change the solution of color to yellow to yellowish brown. After 4 hours, collect the solution in the gel form by use the china dish and heating by the Murphy furnace is 5 degrees Celsius in 1 hour. After 1 hour, the particles after 1 hour to collect the samples and crush fine powder. That is the sample was stored magnesium oxide nanoparticles. Result and discussion. Magnesium oxide was synthesized by the green method from the magnesium nitrate using neem leaves extract. So this is the absorption and this is wavelength. The highest UV spectral analysis of the sample was done the wavelength range of 100 to 800 nanometers, and highest peak is 208 nanometers. This is the detection XRD of the magnesium oxide nanoparticles. White color powder nanoparticles were obtained as powder, and the result of the structure found in the simple cubic nature by using the Darley-Richard formula. Formula is D is equal to K lambda upon beta cos theta. Find the crystal average size is 29.6 nanometer, and that confirms the particles as a nanoparticles. Conclusion. In conclusion, we have seen that the low cost materials are needed and the procedure to easy carry out in any laboratory. The process pollution free, here eco-friendly process, synthesis of magnesium oxide nanoparticles by using the neem leaves extract. Nanoparticle size is 29.6 and energy band gap is a 5.96 electron volt. Next slide. This is the references. Next slide. Look deep into the nature and you will understand everything. Albert Einstein ने म्हटलेलं वाक्य आहे. Thank you. सर म्हणजे कसं आहे की सध्याच्या परिस्थितीमध्ये सध्याचे जे म्हणजे पूर्ण भारतातले जे फार्मर्स आहेत ते जे जर्मिनेशन ऑफ सीड्स आहेत त्याच्या बाबतीत खूप म्हणजे त्यांना खूप त्रास होत आहे. त्याच्यासाठी आपण म्हणजे या नॅनो पार्टिकलचा यूज करू शकतो जर्मिनेशन ऑफ सीड्सची जे इन्क्रीज करण्यासाठी. 200 to 800 nanometers. Uh, 200 to 800 nanometers, and highest peak is at 208 nanometers. नहीं मागची UV lambda is a wavelength 5.1 something 0.94. K is a constant. Beta is a half width full half width full length. ये प्रेजेंटेशन इंडेक्स नहीं है. कोणाला टाकायला काय म्हटलं bulk material of the magnesium bulk material of magnesium oxide. What is the name of the plant? लीला नहीं ये
व्हॅल्यू कशी काढली आपण नॅनो पार्टिकल. तर आपला जो डार्लिस्टिकल फॉर्म्युला आहे ते इज इक्वल टू के लॅम्बडा अपॉन कॉस थिटा. कशाच्या कशाच्या XRT वरून डाटा म्हणजे काय होतं की XRT जी प्रोसेस आहे ती हायेस्ट पीक जे आहे ते समथिंग 40 to 50 तर त्याची जी हायेस्ट पीक आहे ना ते बल्क मटेरियल सोबत मॅच होते. जे बल्क मटेरियल ऑफ म्हणजे गुगलवर आहे आपल्याकडे त्याच्यावरून. ठीक आहे. कन्क्ल्युजन काढता कन्क्ल्युजन. Sir, data of UV to calculate the band gap value. 5.96 electron volt. Formula tau is equal to speed of light c sc upon something. Sir, band gap is 5.96. To use the formula is torque kaitari method. Sir, sorry, my mistake. Sorry, my mistake. मी तुझे clear नाही केला तो समजा. C is equal to speed of light and lambda is given. Absorption. Sir, conductor. नहीं सर सभी कंडक्टर. Thank you.
Next part is please participate and start filling up.
और काढायला लागेल का? क्या आवाज आएगी? विलियम चालू है मोबाइल का. मग याच्यावर चलावला बोला का? लागली का वरती लागली? लागली. आवाज येत आहे.
हेलो.
ऑनलाइन में त्याचा आवाज दाखवता आलते लेकर.
हेलो.
चालू आहे काय?
Yes, sir. Can you hear me, sir? Okay, sir. So my topic is
First of all, good evening to everyone. My name is Harshan Yadav. I am from Veer Bahadur Singh Purvanchal University, Jaunpur. Yes, sir. Can you hear me? Hello.
चालू चालू है हाँ कोई स्टिकर लगा सर वही बेच रहा है
Hello, sir.
ऑनलाइन चालू है
Yes,
इसमें
sir.
भी नेटवर्क प्रॉब्लम आ जाता है अटक जाती है आवाज गायब हो जाती है
Can you hear me, sir?
ये उधर से आ रही है आवाज
Can you hear me? Hello.
Hello, Harshal.
Yes, sir. Can I start now?
Yes.
Okay, sir. So, I have done synthesis of copper oxide nanoparticle by hydrothermal method, and its structural and surface morphological under the supervision Dr. Naveen Chaurasia.
ऑनलाइन उधर से जैसी आएंगी वैसी इधर आएंगी
So these are the index I have included: introduction of nanomaterial, classification of nanomaterial, approaches to nanotechnology, synthesis of method of copper oxide, characterization of
उधर से जो
nanomaterial,
आवाज आ रही है पहले कहाँ है मोबाइल पर
methodology, application, then
इधर एमपी से बढ़ा देता
in the third slide, I have mentioned the introduction of nanomaterial. Nanomaterial, it is a material with a single unit small size, whose size vary from 1 to 100 nanometer, and it can be exist in nature and can be created from variety of products such as carbon or minerals like silver. Most nanoparticles are very small. It cannot be seen with the naked eye, and even with conventional microscopes. Actually, the unit of nanomaterial is measured in meter. 1 nm is equal to 10 power minus 9 meter. 1 billion of a meter is equivalent to 1 nanometer. This is the classification of nanomaterial. 0 dimension, 1 dimension, 2 dimension, and 3 dimension. In 0 dimension, the number of free electrons are bound, cannot be moved freely. They are restricted. Whereas in 1 dimension, number of free electrons moves only in 1 dimension. And in 2 dimension, number of free electrons move in 2 directions, either in x, y, or y, z, or x, z. And in 3 dimensions, they are freely moved in 3 dimensions. These are the examples like nanospheres, clusters are the examples of 0 dimension, nanotubes, wires, rods are the examples of 1 dimension, and thin films, plates, layered structure are the examples of 2 dimension, and polycrystals are the examples of 3rd dimension. Now, what are the properties of nanoparticles? So, I want to tell the properties of nanoparticles. First of all, the metal nanoparticles have higher thermal conductivity if we compare the fluid in stable form. And the second point is nanofluids. Nanofluids are those nanoparticles when dispersed in solvent like polyethylene, glycol, or water. That is termed as nanofluid. Nanofluids show the best properties if we compare it warm transfer fluid and fluid containing micro-sized particles. Because what happens in nanofluids, heat transfer takes place at the surface of the nanoparticle, and it is suitable to use the particle with band complete surface area. And in the third point, I want to tell that it has been proved that nanofluid consists of nano copper oxide nanoparticle in water or ethylene exhibit higher thermal conductivity. According to some literature published, it states that nanoparticle will function fine if their dimensions is less than or equal to crucial value, that is 10 to 20 nm. Because at such a low scale, the magnetic properties of nanoparticle dominated effectively, which make these particles beneficial and can be used in different type of application. Now, what are the approaches of nanotechnology? Basically, there are two approaches: top-down approach, bottom-up approach. I want to tell what is the top-down approach. In top-down approach, it involves the breaking down of bulk material into nano-sized structure of particle. And top-down approaches, they are simpler and depend either on removal or division of bulk material or miniaturization of bulk fabrication process to produce the desired structure with appropriate property. But there are some disadvantages in the top-down approach, that is the imperfection of surface structure. For example, nanowires made by lithography are not smooth and contains a lot of impurity and structure defect on its surface. Now, for bottom-up approach, it refers to the build of material that may be atom by atom or molecule by molecule or cluster by cluster. It has the less wastage and hence more economical. Now, since I have done the synthesis on copper oxide, so I want to tell the physical and chemical properties of copper oxide. Its density is 6.31 gram per cubic centimeter, and in imperial value, it's 0.227. Molar mass is 79.55 gram per mole, and thermal properties of copper oxide. Melting point is 101 degree centigrade, and boiling point is 2000 degrees centigrade. Chemical data is copper CuO, and copper oxide. Copper oxide is light in 11th group, and oxygen is light in 16th group.
Hello, one.
Now come to the chemical composition of copper oxide. So I want to tell the copper oxide contains near about 50% copper and 20% oxygen. Now this is the synthesis of copper oxide nanoparticle which I have made. I have taken copper sulfate 2 mole as precursor material. Then I have mixed it in 100 ml distilled water solution and stirred for 2 hours. Then I have added PEG dropwise, that means polyethylene glycol, and then again stir for 45 minutes. Then add surfactant 10 ml solution which contains sodium hydroxide and distilled water solution. Again I have stirred for 30 minutes, and after that I have dry it at 80 degrees centigrade in furnace for 3 hours. Then after grinding, I have obtained the final copper oxide.
कितने मिनट लगेंगे? 4?
Listen, Yadav,
Yes, sir.
your time is over.
Okay, sir.
तो पढ़ लेते देंगे इनको तो होने ही इनको होना इनको हुनर तब ले बोल तो बेटी गोर तब ले लिखना हां तब ले ये की होना तब देखते दो बेटी है ना उसमें दो मंगे तो दे देंगे आई ना अपने बात काट लेंगे ये मैं कम में आता था हां ये भी डाल दे
Hello. Hello.
Yes, sir.
Is your application?
Yes, sir. I think there is some network problem.
No, you prepared no copper oxide, right?
Yes, sir.
Then what is the application of copper oxide?
So copper oxide application, I can use it in a gas sensor, humidity sensor, and wait a minute, sir. I have mentioned it.
Have you carried out the gas sensing properties?
Sir, I have not done the application part of copper oxide. I have mentioned only applications. These are the application development of supercapacitor, infrared filter, gas sensor, catalysis, semiconductor.
Okay. What is the band gap of copper oxide you synthesize?
The band gap is 4.1 electron volt I have obtained. This is in the graph I am showing to you. This
What is the band gap value?
4.1 electron.
Yeah, if it is a 4.1, then how you use in the gas sensing?
Actually, sir, the energy band gap is higher. So
4.1 is that band gap, no?
yes,
That band gap comes into the conductor or semiconductor or insulator range.
sir, I am not sure about this, sir.
Okay. In XRD, which crystal structure you got?
So monoclinic.
Monoclinic. What is the lattice parameters of the monoclinic?
Sir, actually one angle is 90 degree and the two angle is not equal to 90 degree.
Okay. Your XRD patterns, no? XRD fix are matches with the dissipated data card.
Yes, sir.
What is the meaning of dissipated data card?
The JCPDS card number gives the detail of.
No. What is meaning of JCPDS?
Actually, I don't remember, sir.
Okay.
Any other questions, sir?
Yes, participants. You presented very well.
Yes, sir.
The presentation was excellent and you presented very nice information. Very well, sir. Actually, we both are looking towards your research work. Actually, there is no matter of sciences, but you are doing very nice research. This is important thing, and that's why I am going to congratulate you for your this career in the research. very tough to us to judge you because all of you presented very nicely. Recently, the things that important. That's why all of you report the very seriously.